and you have been like so productive in 3D printing. Do you have any tips like for your success in research and mentoring students, to share with us?
I think the main thing for me is, with students especially, I like to figure out first what their interests are, what they're interested in, because I think the best way to get someone to work hard and go to the lab and stuff is to pair them up with projects that they're really excited about, So the first thing I do is try to get good people, of course, recruit good people. And then once we do that, figure out what their interests are and pair them up with a project that I think that they'll be motivated to work on. And then I basically just let them kind of, which is probably what you do too. I mean, sort of explore, basically sort of give them some freedom to explore, the direction that the project takes them instead of try to, micromanage or dictate, I mean, of course we provide feedback and we have group meetings and subgroup meetings and stuff, but I feel like less is more, especially if we're trying to find new things and innovate and whatnot. I mean, the best innovation comes from the student, not from me, right? I stopped having ideas like 10 years ago. But I mean, that's the good, so that's the interesting thing about our job, right? Which is once you train a student, then they leave, right? So that's the bad thing. But the good thing is that, you always have new people coming in, so it sort of refreshes, so it's never stale, right? It's like always refreshing with new excitement and that sort of thing. So, I mean, to get the best students, you have to sort of create a good atmosphere and, positive environment as much as possible. So, yeah, so that's probably what you do too, right? I guess, because you've been extremely productive as well, right? So.
Well, I was very much inspired by one of your presentations I heard like during the MRS meeting. You said that YouTube was one of the greatest source of inspiration. and because of that, I started to watch YouTube more often than before. And indeed. Yeah, so
that's when you started getting all those Nature papers, right?
Well, yeah, I also was very lucky to have some outstanding students in my group.
Yeah, Mike, so you did a PhD at Harvard, right?
Yeah, with Charlie Lieber.
Oh, Charlie.
Yeah.
Oh, okay.
So, so that was, I think that was a great experience. So, I got my degree in chemistry.
Yeah.
I've been in mechanical engineering this entire time, and I'm probably more of an engineering mindset, but my original bachelor's was at Brown in chemistry. So there were some amazing people at Brown, like Rich Stratt, these molecular dynamics people. And then my first research experience was with Andrew Rapp, who does density functional theory at UPenn, also in chemistry. And I spent the summer doing DFT of lead zirconate titanate, PZT. So I was doing all these DFT calculations, but that was before I took quantum mechanics. So the next semester after that, I took quantum mechanics, and I did really well because I spent the whole summer learning it. And then I wanted to do chemistry, but I saw Charlie's talk when I got to Harvard. I saw Charlie give this talk on he wants to pour. This was in 1999 or 2000, right, when the computer era was really taking off, and he said he wants the next computer to be something you can pour, basically like pour nanowires to make a computer. And I just thought that was an amazing idea, and that's actually what we ended up doing really in Charlie's group. So so that was an amazing experience, I think. I mean, Charlie was always available to meet with us, and despite how busy he was, and
So
and then I postdoc with Jim Heath at Caltech. Jim Heath, he was Rich when they discovered buckyball. He was the grad student who, at the time in the group with Rick Smalley, who was part of that discovery. So.
Yeah, I noticed that Nature paper. He was the second author of that paper, of the Nobel Prize winning paper.
Yeah, so maybe, I don't know, maybe he should have, but they can only give the prize to 3 people, right? That's the problem. So, so they gave it to, there's 5 people on that paper, right? Kroto, Curl, and Smalley. Those are the 3 that won the Nobel Prize. But then Jim was the second author, and then O'Brien. Anyway. But there's a
Mike,
there's a video on YouTube actually. It's like 40 minutes long on the discovery. It's this amazing interview with Rick Smalley and Kroto and all these people. I teach this class, Introduction to Nanotechnology, and I show that video on the discovery of. I mean, they weren't out looking for buckyball, right? They were sort of modeling carbon-rich stars and whatnot using mass spec and. They discovered it by accident. They just saw this peak at C60 and they said, what's that? So.
Can you had a question?
Oh, sorry. So Mike, unfortunately, I missed your MRS talk, as Sheng mentioned, in which you talked about that you should watch YouTube videos. The EML webinars, we are actually doing the live streaming in YouTube as well in our channel. Do you mind elaborate a little bit about your presentation on that part? Why the researcher should read and view the YouTube more often than before?
I think I was probably joking, but I do think, one thing I've noticed is, is I think if you spend all your time working, right? If you work too hard, sometimes that's not good for creativity, right? Sometimes sometimes you can solve problems. I mean, Zhuang Zhou is the master of solving problems in the most elegant possible way, but sometimes you can solve them without by taking a break, right, instead of working. And so I learned that in college, that if I took a break and went out for a walk, and I was trying to work on this homework problem and I couldn't figure it out, if I just took a break and went for a walk, usually when I got back from the walk, I would sit down again and suddenly know how to solve the problem. So I think that's why I try not to be too top down with my students, because I feel like you don't know when they're going to solve the problem, right? It may be when they're at home watching TV, So, so I think we don't know exactly how our brains work in terms of solving problems. But sometimes if you stare at the problem too long and try to force your way through it, that's not. Sometimes it works by not trying to do that, right? So, and I also learned that actually when I was in the chemistry lab. I did inorganic chemistry as a senior at Brown, and I was trying to get crystals to form, and I couldn't get crystals to form, and then I took a week-long vacation, went home, and then I came back and the crystals were, because it was a slow evaporation, and during that week, and the crystals were there when I got back. So so sometimes by stepping away from things, you can actually solve complex problems, so that's my opinion. I don't know how you guys feel, but
well, next time you can ask your student to watch your YouTube recording of your EML webinar to take a break.
I don't know if that'll help or not. That's they need to watch something totally different, right? Like whatever, music or cats or something. And
let me introduce. Maybe you have met Jimmy Xia, right?
Right.
I don't know that we've actually met, but of course I know who Jimmy is. So.
Yeah. You received an award. Is that right? EML
Young Investigator Award, right?
Yeah, that was amazing. I think that's right when the journal was getting started, and yeah, it's amazing that you guys set that up and helps with that and everything. So yeah, the journal has really taken off. I mean, we've published 3 papers there, and just the quality of the papers is just amazing. So the 3 of you, right? Jimmy, Zhuang, and John Rogers.
Yeah. Submit more papers, Mike.
And Wen Li are also two editors. So these two young people actually started the idea, and they felt they need have some older people to help. They recruited us.
Hey, Mike, nice to see you.
Who's that? I can't.
This is Sulim from Penn State.
Oh, hey, how's it going?
Good.
Hey, Surin, good morning.
Hey, morning.
Hey, Jimmy. Hey.
Hi, Sheng. How are you?
Good, good.
So, Mike, back to your nanotubes. So you did nanotube at Harvard, but the first work I actually knew of your work was ear. It was all over the news. You made ears. So from nanotube to ears, how did that happen?
Well, actually, so in Charlie's group, he was working on nanowires, and we took the nanowires and we put them on plastic. And so we made a ring oscillator on plastic, and so that was really, that was right around the time that John Rogers was getting started at University of Illinois. So he was doing the transfer printing, and we were doing the nanowire flow stuff on plastic, and so that was sort of going head to head there, and both of them worked. I mean, both of us were able to get pretty high frequency ring oscillators and stuff, and start to integrate single crystal silicon on plastic using these two completely different methods. And so from a chemistry standpoint, I mean, it's really engineering, but it's not even mechanical. I mean, it's electrical engineering. But I sort of thought of it sort of like a chemistry standpoint, sort of this merger of inorganic and organic, which I think is sort of how John Rogers thinks of them too, right? He's talking about merging electronics with biology, which is basically inorganic with organic. And so eventually, so that was at Princeton. I was assistant professor there. And we, the first thing we did actually is we used John's method to print PZT, because I had learned about PZT, during my with Andy Rapp, right, at UPenn. And so as I mentioned before, and so I was printing PZT onto plastic, and then we thought, can we take this to the third dimension? And that's when we did the 3D printing stuff, and thought, can you create electronics and biology hybrids in 3 dimensions rather than sort of 2 dimensions? And that was just a crazy thing. I think that I mean, there was like because you were at Princeton, right? Sort of the middle of farmland, and there's not a whole lot of stuff to do there. So like you come up with these sort of nutty ideas there, and so like so we just came up with that, but actually, I think it sort of set the foundation for a lot of the stuff we're doing now. I mean, it wasn't like the most sophisticated example, but it was sort of this idea, can you merge electronics and biology in 3 dimensions using the same 3D printing tool and not use a clean room facility at all, right? And so since then, we haven't used the clean room, and we haven't had to pay for clean room user fees, and saved a lot of money there. So, but yeah.
I remember your like stretchable PCT ribbons, for energy harvesting work. Yeah, I read that paper very well. So, Mike, I got a question. Like, you have been making so much progress in 3D printing. I'm sure you will talk about those opportunities and challenges later. What are the key challenges in the field of 3D printing right now?
That's a good question. I think there's lots of challenges. I mean, I'll talk about some of the materials challenges later. The materials integration stuff. But for me, I think one of the bigger challenges, which no one really talks about, is how do I convince the average person to go out and buy a 3D printer? So, I mean, that's a question that I've had for a while. And I mean, everyone has electronics is now commonplace, right? So everyone has a laptop and a cell phone and a smartwatch. But the question is, if 3D printing truly is the next thing after electronics, if it is, and I think we've shown that there's some interesting capabilities, but if it truly is, then the question is, what is going to be the application where my mom or my aunt or uncle or someone is going to go out and buy a 3D printer? I don't think we have the answer to that right now. I mean, even when I ask students, I mean, when I give talks now, especially to high school students, right? I say, how many of you know what 3D printing is? And by now, everyone raises their hand. That wasn't true 10 years ago, but by now, everyone raises their hand. All the kids know what 3D printing is. And then I say, well, how many of you have used a 3D printer? And at this point, actually, most of them still raise their hand. And the reason is because they use them in their school. They use them primarily to make like mechanical objects and that sort of thing. But then I say, how many of you actually own a 3D printer? And then pretty much no one, even among the kids, no one has their hand up. So the question is, what is going to be the killer application of 3D printing that the average person is gonna need one? Or is it maybe it's not the next wave? I don't know. I mean, just because we're working on it doesn't mean that it definitely will be. So I think for me that's one of the bigger questions. Is, I mean, we've seen it can do all these amazing things, but what does the average person need it for, right? So I think until we answer that question, I mean, I think, of course, there's been aerospace and automotive applications and things like that, and some biomedical. But we have Boston Scientific, one of the largest biomedical companies here, and I've met with some of the leading researchers there, and I say, do you use 3D printing at Boston Scientific? And they say, yes, we have this big 3D printing lab and all that. And I say, well, what about in your products? And they say the only product that has 3D printing is then they show me some small metal piece in one of their products, and that's 3D printed. And none of their other products actually have 3D printing in it. So the question is, what is going to be really the use case for 3D printing, both at home and industry as well, right? So I mean, we can publish lots of interesting papers, but what's going to be the thing that the person really needs, right?
Shulin, you had a question?
Oh yes, actually Michael's later statement actually clarified my thought, my question. So I was about to ask this question: what kind of product 3D printing can print, and we cannot manufacture by other means, right? I think that's really the question. Are there any products that 3D printer can print and have good properties, material properties, geometry, etc., right?
Yeah, exactly. I mean, it is being used in some custom applications, right? But you're absolutely right. I mean, from a mass production standpoint, I mean, molding and metal forming and these sort of traditional techniques, they work well, of course. And but for custom applications, you can see the advantage. So I think in my mind, what would be exciting for me is just like electronics has sort of electronics has been democratized in a sense that we all have these electronic devices. I mean, maybe what it is that biomedical devices, will be democratized, and everyone has a 3D printer to print their own biomedical device at home, and then it's merged with a surgical robot or something, so everyone can do their own surgery and robot and biomedical implants and stuff like that at home. I don't know. I think we've sort of been focused on the biomedical space because we have these companies here, but I mean, 3D printing is used in the automotive, for making parts for automotive and aerospace and all that. But even then, I mean, you look at composites, right? I mean, in airplanes, I mean, they're not made by printing; they're made by the traditional carbon drawing and then epoxy laminate method. So I mean, that's really the question. If you can merge it with maybe surgical robots, so that you can both do the surgery and implant a biomedical device at the same time, maybe that's the future.
Or perhaps they will be used for large office space. Maybe a big office, one floor would share one of these 3D printers, and when people need the office supply, the secretary just go there and print something and bring it back.
Yeah, I guess Sheng asked a very good question, and Mike, in your answering that question, you referred to that we have the computer, we have the iPhones, iPad, and all the tablet and all the wearables. Should 3D printer be in each house? I think the key differences over there is that those devices, the content they provide is still digital, but for 3D printing, you are really printing physical stuff. For example, I do have a 3D printing in my house. I bought it as a birthday gift for my boy to keep him busy during the pandemic. But it takes a long time to learn and really print something meaningful. So learning curve is actually still steep. I mean, in the long run, if you really want every house to buy one, I think that's the challenge there. The speed, the cost.
Hey, Mike, Sigurd Wagner is here from Princeton.
Oh, hey, Sigurd, how's it going?
Oh,
So Sigurd and Qigong were the first people really to put amorphous silicon on plastic and polysilicon on plastic, and with Stephanie, right? So I mean, those were the papers I read when I was in.
Yeah, there are two different things. One is on non-stretchable, well, basically rigid plastic, and the other one is on soft stuff. That these were two different phases. But I was lucky enough that Qigong was during that period down the hallway. And there's nothing more valuable to an experiment than a theorist who is willing to listen to you. and Qigong is one, Yeah. Hi, Mike, how you doing?
Good. How are you?
I'm fine. It turns out there's so many interesting webinars that I can spend my entire day in just sitting here. I have many interests, but I still stay engaged in the larger electronics group in the university. I'm kind of a fifth wheel on it. I can claim that my brain is still working.
Do you still have those samples in your office there?
Yeah. It turns out I still have the office, and currently, officially, I'm not. I kind of, there are these lockdown rules, but I figured in this period you start reflecting on what you should do, and one thing I should do is finally clean up my office. But I'm not officially authorized to go in long enough. You have these rules.
We ask you to share your screen. We will have continue this discussion after you
afterwards.
Oh, okay.
We'll take it over. Introduce Mike when he's set up.
Sure.
But I look back, Sigurd and Qigong's paper, so that was 2003. So we published our nanowire plastic paper 2003, and then John Rogers published his first transfer printing paper 2004, right? So that was all around the same time that we were all doing that stuff. So, and then I think, but Whitesides did the stretchable gold stuff like 1998 or something. It was pretty early, right?
Yes.
All right, so I guess you can see my screen.
Yes. Can you put it in full screen in the display mode, presentation mode?
Sure. Okay.
Okay. Good morning, good afternoon, good evening, everybody, depending where you are. Today is my great honor and pleasure to introduce Professor Mcalpine. And he really does not need much introduction. So to be brief, he's a Kumar Family Chair Professor of Mechanical Engineering at the University of Minnesota. He has taken a starring trajectory in his academic career. Got his BSc in Brown and PhD in Harvard and a postdoc at the Caltech. He has been doing exciting research in 3D printing and for many biomedical applications. His research has been covered by a lot of high-profile media reports, and he has also received quite a lot of awards. So I'm not going to embarrass him to go through the list. So most notably, he has received the PCASE, which is denoted as the highest honor for this junior research faculty and also this NIH Director's New Innovator Award. So, so this is written on his bio, but what is not written on his bio is that he's also a very effective educator. He has educated quite a few faculties from his group. And actually, I'm a friend with quite a few of them who has been doing very well. So without further ado, Mike, it's all yours. We are excited to learn your latest advances.
Sure. And, you know, I'm not sure what the format is, but actually I don't mind if people want to interrupt and ask questions now and then. But basically, what we're working on at the University of Minnesota, which you can actually see behind me, as you'll see in a second, this window faces the university of my apartment here. And basically, we're working on these 3D printing of functional materials and devices. So basically what we're trying to do is expand 3D printing sort of beyond the hard plastics that are traditionally known, and the metals and composites and ceramics, into what we call functional materials and devices, which to us basically means things like electronic materials, and that can include active electronic materials such as semiconductors, and biomedical devices, things like ionic hydrogels, which Zhigong was a pioneer of, sort of translating that to the 3D printing stage, and there's actually a perfect marriage of those two. And soft materials, things like silicones, which is a thermosetting material, and so therefore not traditionally used with the 3D printers, which print thermoplastic materials, and biological materials as well. And not only printing each of these materials, expanding the toolbox of 3D printing, but also trying to merge them all on the same platform, basically. I mean, if this single platform can print all these different materials together and print them in three-dimensional space, then you have something that can do, sort of beyond what photolithography does, which photolithography is focused on single crystal silicon and two-dimensional planar devices, which works extremely well. I mean, you can have transistors now, or you can have processors now which have, many millions or billions of transistors on them of single crystal silicon, and that's not something we can do with the 3D printer. But we can go to the third dimension, and we can integrate soft materials and biological materials and electronic materials together in three-dimensional space. And so the question is, what might that be useful for? And we have some ideas, but it looks like, the absolute incredible expansion of 3D printing in the last few years has shown that many people have ideas in this space. And so it seems almost limitless, but at the same time, we have to be careful about what exactly we can use this technology for, and what the real most important applications are, right? So, as a way of background, actually, the first time I heard 3D printing I was late to the game because it's been around since the 80s. But I heard about it in 2011. I attended one of these Frontiers of Engineering conferences, and Hod Lipson was giving a talk on 3D printing, and I just sat there amazed. He also was not printing hard plastics. He was actually putting flour and food coloring in the printer, and so he was printing food. And then he had this muffin where if you cut the muffin in half, there was like a letter written on the inside of the muffin, in food color. And so I just sat there amazed, and we went back and said, we have to start working on this, and see if we can integrate interesting materials into this platform. So also by way of background, so I live here. So this is a sunny day, which is what it looked like a week ago, and yesterday we had a major snowstorm. But so we're in winter now. We're in 6 months of winter after 6 months of summer, and you can see on the left there that so I live right across from the university, and you can see the river cuts through. So outside my window here, that's the view that you have, and the downtown Minneapolis is to the west there. The university is across the river on the east, and then St. Paul is all the way on the far side of this map on the east. So we're the twin cities, Minneapolis and St. Paul. And So that's the Mississippi River. It starts in Minnesota and travels all the way down the United States, but it does start in the upper northwest of Minnesota. And so basically, I can walk to work every day. It's beautiful, well, except when it's 10 degrees outside, but I still walk to work. And just an amazing place, because in the image on the right, you can see the photograph on the right-hand side that tall beige building is actually the medical school, and it's right across the street from our engineering school. So I can go across the streets. We have underground tunnels too, and we can collaborate right with the medical folks. And they're always willing to collaborate and figure out new applications of 3D printing. The Twin Cities are the home to large biomedical companies. Medtronic, the pacemaker, was invented in Minnesota, and Boston Scientific, and these companies also like to collaborate with the U, which is amazing. Target is headquartered here. Seagate, so all these amazing companies that like to work with the university. I should also mention, I thought Ziguang might like this. We have some weird things around the Midwest here, and so one of them is this. So this summer I drove to this house on the rock, and this guy, Alex Jordan was his name. So it's a 4-hour drive. It's right outside Madison, in the forests of Wisconsin, and he built this house on this rock here in the middle of the forest, and it's on this deer shelter rock, and the rock is 60 feet by 70 feet by 200 feet high in the Ozark National Forest. And the interesting thing is it has this interesting mechanics feature here, which is this protruding infinity room, as he calls it, which is not there's nothing holding it up. There's no support network. It is counterbalanced by tons of concrete, but it juts out with no actual support mechanism that's visible out into the forest. And if you look on the right, you can see it looks like you're looking out into infinity when you walk in. It sways, actually. It's kind of scary because it sways as you walk out. And he put this little trap here where you can stare straight down into the forest. So it's 218 feet long infinity room, and made in 1985, which is a triangular shaped steel truss counterbalanced by tons of concrete, and extends 140 feet beyond any supporting structure and 15 stories above the rolling hills and valleys below it, and with over 3,000 windows. So it's worth a visit if you ever make it out here. So okay, so I think we are in a mechanical engineering department, and there are a lot of people in our department and other mechanical engineering departments sort of focus on this problem of robotics, right? And making robotics more and more like humans. Boston Dynamics is a great company that works on that. That's where this robot came from. But, we've sort of been interested in this inverse problem for a while, which is, can you take humans and make them, instead of making robots more like humans, can you actually take humans and make them more like robots? And, maybe 10 years ago when I would say this, it would elicit, quite a response. But now this is commonplace. I mean, everyone wears a smartwatch, and so everyone is basically bionic, right? The average person has the entire world's information of human existence on their wrist. And, but it's not just it's not just for the electronic era. I mean, but a lot of these devices are electronic. So things like the cochlear implant is sort of the classic example of, they have this electrode that's threaded through the cochlea and is able to restore hearing after it's been lost by basically stimulating the nerve endings there. So that's sort of an early example of a flexible bioelectronic interface. And of course, things like pacemakers and prosthetics, and then the sort of new generation of bionic eye implants, which are originally they were stimulating the retina, but now they've actually moved the electrodes directly into the brain. to try to stimulate the visual cortex. And then, of course, things like what Stephanie LaCour is doing with these e-dura, right, the electronic dura to stimulate spinal regeneration and whatnot. So the point here is that, electronics merged with the body have regenerative applications, but it can also have augmentation applications as well. As we look at the smartwatch, that's sort of the direction that things are going in. If one has a cochlear implant installed on their head, then in principle that gives them the ability to also expand the range of hearing beyond, the normal range of hearing, which is 22 hertz to 22 or 20 hertz to 20 kilohertz, right? And in fact, I know people who wear cochlear implants. They say they can plug their phone directly into the implant and basically skip the mechanical part, right? Skip the microphone and the speaker and the microphone, and just have a direct electronic communication between the smartphone and your brain, in a sense, by plugging the phone into the cochlear implant. And in fact, some of the people who wear cochlear implants now, they tell me that they have Bluetooth in the implant, so they can Bluetooth from their phone to the implant, and so wirelessly connect to their brain from the phone. So this is the direction things are going in. And I call this Human X. That's the term I came up with, like the iPhone X, the Human X. And but the question is, and this is the question, that Ziguang and Sigurd have been asking for 20 years now, right? Which is, and John Rogers as well, which is, if one wants to integrate silicon or electronics with the body, what are some of the issues with doing that? And of course, one of them is the mechanical mismatch. Silicon is a single crystal 100 gigapascal Young's modulus brittle material, whereas skin is soft, flexible, and stretchable. And but the thing is, there's also the fact that the silicon needs to be crystallized to be a single crystal. So that's a temperature requirement of over 1,000 degrees C, which is completely incompatible with biology, which can only withstand, DNA can go up to maybe like 40 or 50 C before it denatures and stuff. So, but then there's also the dimensionality mismatch. All of photolithography and semiconductor processing is all planar, right? And the biology from the scale of DNA, proteins, all the way up to organisms, it's all three-dimensional, right? So there's that dimensionality mismatch. It's okay for a smartwatch when you have this sort of two-dimensional interface, but if you could take it to the third dimension, you might be able to sort of grow electronics and biology together on the same common platform. And actually, a lot of people don't know this because a lot of people haven't even heard of Minnesota, the state. But although this election cycle, we've been getting a little bit of attention. But this 3D printing technology was actually invented here. The stereolithography was not, of course, but the FDM, fused deposition modeling, was invented by Scott Crump, who founded Stratasys, and Stratasys is also headquartered here in Minnesota. So the FDM technology, the thermoplastic printing, where you melt and extrude a thermoplastic, was invented here in Minnesota, or at least commercialized by with Stratasys. And so, but we want to sort of, even hard plastic can have a Young's modulus on the order of megapascal, which is still orders of magnitude higher than your skin, right? Which is on the order of kilopascal. So that's some of the. So the question is, if you want to sort of overcome these discrepancies here, maybe a next generation of 3D printing tool can do that, because we can print in three-dimensional space. So we can print in the same dimensionality as biology, which is three-dimensional. We can merge soft materials and electronic materials together on the same platform, so we can overcome some of these mechanical discrepancies. And also, unlike the FDM printing, where you're heating and extruding, we actually print typically at room temperature by exploiting shear thinning effects. And so we can basically incorporate functional materials and biological materials on the same platform because we don't have these heating requirements. So we, in principle, overcome the three dichotomies that are mentioned at the bottom of the slide. And our printer that's set up is one that we custom built. And we set it up back in 2015. It's basically an Aerotech motion control stage, and then we mount these syringes on it where instead of using heating of a thermoplastic and extruding, we just use pneumatic extrusion. And then sometimes we do UV curing, like if we're printing silicones or ionic hydrogels. On the same comment, the thermoplastics are replaced with inks, right? So we're basically can have multiple nozzles printing multiple types of inks on the same common platform, all pneumatically dispensed. And you can image the entire process. And to be honest, I used to think that this is the most important part of the 3D printing technology. And as I'll show later, I've realized that the most important part of the printing technology is the one that you don't see, which is the computer, which controls everything. So, I sort of see printers now less as manufacturing tools and sort of more as robots, part of a larger robotic system where the robot may be involved in subtractive processes and additive processes and artificial intelligence, and tracking and whatnot, all on the same common platform. And the nice thing about this platform is, from a scientific standpoint and engineering standpoint, you can merge many disciplines on a single platform. I mean, you have biological, biomedical, electrical engineering, mechanical engineering, manufacturing, computer science, chemistry, and the formulation of the inks, all on the same common platform. And it's amazing because we have students who are brave and they want to work at this interface and work at this interdisciplinary type of field, and lots of exciting things that in principle can be done here. And another concept here that we've sort of introduced is this idea that in addition to multifunctionality, in principle, it's also multi-scale. Now, we can't print at the nanoscale because the nozzles, in order to really print something, you have to be able to extrude through a nozzle. And so there's only so much shear you can apply before you damage the material or damage the nozzle. But we do use nanoscale inks. So the ink can be at the nanometer scale, especially for incorporating functionality. And then we print at the micron scale, typically 10 to 100 microns or higher. And then we build devices which can be as large as, foot by foot by foot, right? Cubic foot. And so we start with our functional nano inks. We print at the micro scale, and then we can develop macro scale devices. So from that sense, it's a multi-scale and multifunctional platform. Okay. So the remainder of my time here, I'm going to focus on some specific things we've done, and this is just sort of some highlights, really. I mean, because and it's not just us, of course. Now many people are printing lots of different types of things, but these are some of the things we've done recently that I'm excited about. I'll start simple and then build complexity. And so one of the early things we did, sort of this low-hanging fruit, is organ models, right? So because we're in this biomedical arena here in the Twin Cities, and we were sort of inspired by some of these papers, which say that surgeries, of course, come with risk, right? And this British Medical Journal is sort of infamous statistic here that medical errors are the third leading cause of death. Whether that's true or not, I'm not sure. Especially now, probably coronavirus is the third leading cause of death. But there are risks associated with surgery, and there's many reasons for that, of course. But one of the reasons is that the doctors rely on two-dimensional images. I mean, they rely on CAT scans and MRI scans, which is 3D data. I mean, at the end of the day, it's 3D data, but it's represented in two-dimensional format for visualization. And then they go to the surgery and they sort of had to improvise or sort of piece together in their mind what the three-dimensional organ might look like. And, this is an arena where 3D printing can play a role, because you can basically take that 3D data directly from the patient and print organ models that replicate the anatomical structure of the actual organ that's going to be operated on, right? So the doctor can analyze it in advance, plan the surgery. Residents can use it for practice. And in fact, there are some papers which show that there are some statistical improvements in accuracy in patient selection, helping the patients themselves understanding the surgical procedure, reducing the operation time, and reducing blood loss. All, of course, together in principle should help reduce surgical complications. But the only problem with this is that these organ models are built around hard plastics. So you can't cut into them, you can't suture them. They don't feel like the organ. They're just, they replicate the anatomical geometry, but they don't feel like the organ. They don't have any functionality built into them. And so, believe it or not, we were the first group to publish this idea, 2 years ago, that you could print a soft organ model. And now this is actually sort of a commonplace idea, but this was the first publication where it was actually demonstrated, where basically you can use, instead of using the hard plastics, you can use soft silicones to print an organ model which replicates the tissue mechanics, and then also build in some of these advanced functionalities like electrical sensing so that it can give you quantitative feedback. And in fact, these tactile sensors are built around Ziguang's ionic hydrogel, as you'll see later, but merged onto a 3D printing platform, okay? And this is realized by the fact that these hard plastics like ABS that are typically used in 3D printing, I mean, they have Young's moduli that are on the order of megapascal or even hundreds of megapascal. And there are some of these developing materials, these sort of tangos and the Ninja Flexes, which can reach down to low megapascal or maybe high kilopascal. But some of the biological tissue can be on the order of 10 kilopascal or less. And so if you want to replicate that, then you really need a soft material, something like silicone or hydrogel or something like that, which silicone is a thermoset, so it can't be melted and extruded, right? So it can't be merged onto the Stratasys platform, at least not right now. I'm sure in the future they'll find a way to do it. But with our platform, because of the shear thinning properties of silicone, we can print silicone pneumatically. And so we basically developed these inks which combine silicone grease, which is a soft bulking agent, with silicone sealant, and that provides some degree of vulcanization or cross-linking, with some other additives to basically print the organ models that are soft and are more tissue mimicking than the hard plastics. Basically replicate the feel of the organ. And so this is an example. Again, the great thing about the University of Minnesota, we collaborated with a urologist on this. He got us the MRI data of 3 men who were undergoing prostate surgery. They had tumors in their prostate. They were having their prostates removed. So we got the MRI data, and we converted that MRI data, segmented it, converted it to 3D data that could be printed, and basically print these silicone inks that I described before, which are, the nice thing about these are solvent-free. They actually don't warp over time. They retain their softness. You can print multiple materials here to create the interior structure. You can use sacrificial materials that can be removed at the end of the process. You can add coloring agents to replicate the color of it and build up. So this is one of our early examples, this sort of simple prostate thing. But we also did an MRI scan of our printed prostate and found that there was a close match anatomically with our printed prostate and the original prostate that we got from the MRI scan. But in addition to that, and this is the amazing thing about University of Minnesota, which is the prostates were removed from the patient, and then my postdoc was there to get the samples, the tissue samples, right as they were being removed from the patient, so we could take them and we could do mechanical tests on the actual prostate tissue samples with 3 human subjects, and they were being removed anyway, which meant we didn't even have to go through the human subject process. And so we could just collect these samples and do mechanical tests on them, to determine their mechanical properties. And so we had those 3 tissue samples. We had the 3 tissue samples, and then we developed 3 inks that could be tuned so that they could basically mimic the mechanical properties of the tissue samples. as you can see, in the low strain regions. We don't yet have the ability to do strain stiffening behavior, but we're working on things like that. And then we can also sort of replicate the color of these organ models by adding dyes. So the point here is that not only does it replicate the organ anatomically, it also replicates it mechanically based on our own studies with the actual patient samples. We gave these to some urologists here, and they actually found them useful. Believe it or not, they were like sticking endoscopes inside of them, and then you can do things which you can't do with the hard plastics, like suture them, and basically do practice surgery on these models. And again, we've had these sitting around our lab for years now. We have kids come in and they play with them, and they don't harden. They haven't warped over time. It's they maintain their integrity. But this is all very simple. I think what we really wanted to sort of build complex functionality into it, and we were inspired by Ziguang's paper, where he's building these ionic hydrogels. Where the point here is that they're transparent, they're stretchable, biocompatible, and then the other key point here is that you have this ionic hydrogel, which is and this dielectric, which Ziguang used 3M tape. 3M also headquartered in Minnesota, but the point here is that the capacitance of that double layer at the electrode is much larger than the capacitance across the dielectric. So the voltage drop occurs across the dielectric, right? So you don't have issues with degrading your interface or the electrolyte. So, and Ziguang basically demonstrated this actuator where by spreading ions across the sandwich there, it forces the ions attract, and then it forces it to compress and then stretch out due to Poisson ratio. And so we wanted to translate this to our 3D printing platform by basically printing the entire structure. And so the tape can't be 3D printed, but we can replace it with silicone. And we can use the same silicone that we use in the organ model, so that the entire structure basically replicates the same softness of the organ model, basically blends into the model. So we basically 3D printed the ionic hydrogel here, and the difference. There's one other difference, which is we use polyacrylamide, and then the ions that we use actually. So Ziguang used sodium chloride, but we had to print this structure, and it takes some time to print it, and so it can dry out. And so we switched to potassium chloride because it's hygroscopic, and but then it's sandwiched with a silicone dielectric in between, and then we put these copper leads on it. So this not only can act as an actuator like Ziguang showed, but also as a sensor. And so we can basically do a calibration curve with the applied pressure and measure the capacitance of the structure, so that then we can print these things and then incorporate them onto our soft organ model, so that you have this electrical feedback, right? So as you're basically operating, do this faux operation on the organ model, it'll actually give you a quantitative feedback based on these 3D printed ionic hydrogel sensors that are incorporated on the model and also inside the model as well. So now we're sort of building complexity here. We go from a single material, the silicone of the model, to now multiple materials that are printed here, including ionic hydrogels, the model, the supporting structure, brought together into this structure here. And as a separate paper, this was published in EML. Actually, we wanted to demonstrate that we could also 3D print an electrically driven actuator, and so this was the difference here is we added this passive layer, so that instead of it flattening like Ziguang showed, it actually will bend. And the way we were able to do this was we incorporated barium titanate particles in the silicone as a composite. And so this was printed, the entire structure was fully 3D printed. We print this, the ionic hydrogel and then the silicone dielectric, and then we use benzophenone to, and then activate it with UV to print the top ionic hydrogel electrode in order to bond it to the underlying silicone and create a full structure here. And as I mentioned, that silicone contains barium titanate particles. So now there's multiple materials, all built into this 3D printing process. The entire structure was 3D printed. So again, we use polyacrylamide here. We use the benzophenone photoinitiator. We're replacing the sodium chloride with lithium chloride so it doesn't dry out during the printing process, which may take, an hour or several hours. And, so this is what it looks like as we're printing this this structure. So same type of sandwich structure that Ziguang showed, but now fully 3D printed ionic hydrogel silicone with barium titanate, and then another layer of ionic hydrogel on the top to create one of these ionic hydrogel capacitors, but used as a sensor or as an actuator. And you can see it is actually, of course, it becomes somewhat opaque with the barium titanate, but it is actually still flexible and stretchable, and so it's under UV the entire time in that video. And believe it or not, this does actually work. So this is an example of a fully 3D printed electrically driven sandwich ionic hydrogel based actuator here. So you can see it does require large voltages, of course. This is ions instead of electron capacitor. But as we build this up, we can actually eventually get to up to a full centimeter of actuation here. So my student was very excited when when we realized this this device here. Okay. Okay, so we're almost there. There it is. All right, so that was that's some fun things we can do. More recently, actually, we've been working with Medtronic. So if I play this video here, can you hear that audio?
No, not right now.
Okay, so let me unplug and then I'll replay.
Valve system serves a broad range of patients with severe aortic stenosis, a narrowed heart valve that is unable to open and close properly. In the catheter-based procedure, a physician makes a small incision through either the leg, upper chest, or shoulder and guides the new valve into position to replace the failing aortic valve. Once in place, the core valve system's self-expanding nitinol frame enables physicians to deploy it in a controlled, accurate manner. After expanding, the new valve takes over the native valve's function to ensure that oxygen-rich blood flows efficiently out of the heart. Patients at high risk for open heart surgery who are treated with a minimally invasive core valve device have a greater chance of survival at 1 year compared to patients who undergo surgery.
Okay, did you hear that?
Yes, fabulous.
Okay, good. So actually, we did pair with Medtronic on this most recent project based on these organ models where they wanted to figure out, this is a minimally invasive surgery, so it's not an open heart surgery, but even with these minimally invasive surgeries, there's some issues with placing these valves and sizing the valves correctly. And so if we could basically create organ models that replicate the patient's anatomy with internally integrated sensors, that we can help them with that process, to make the minimally invasive surgery go more smoothly. And this can prevent things like leakage around the device or regurgitation through the device as you replace the aortic valve there. So this is a more sophisticated model that we published recently in Science Advances, where now basically we're building multiple inks into the structure. And that also includes calcified regions based on a spackling material here, where we're basically replicating the calcification in the patient's aorta in a diseased patient. And so now you can see we have inks that replicate the myocardium, supporting ink structures, which is basically a pleuronic that's removed at the end of the process. And we can recreate the leaflet structures. We can create the calcification sort of in this multi-nozzle approach here. And so we did see actually that when we do some of these hemodynamic studies that the calcified structures do actually require more pressure than the non-calcified, basically replicating the patient's disease. And once again, we incorporated some of these ionic hydrogel sensors into the model, but this time, instead of being printed separately and then sort of taped onto the, pasted on the model like we did with the prostate, now basically we're at a point where we can integrate these devices. So this is a 3x3 array. So this is 9 of these sensors fully integrated into the model. And you can see here that it's built up. Those are the 3 dots on the right-hand side. As we build the model, we can essentially build these ionic hydrogel electrodes directly into the model. And those will basically act as sensors to give us feedback on how the TAVR device is placed into the valve before the surgical process. And again, once again, the silicone dielectric in the ionic hydrogel sensor is actually the same silicone used in the model. So the sensors basically just blend straight into the model. They don't affect the mechanical properties negatively at all. Okay, so and this actually helped us when we worked with Medtronic to. We did some studies here where we were able to basically place these valves into the model, and using the quantitative feedback from the sensors actually helped determine the sizing and the placement of these valves directly into these models, which in principle should help as we, help with patient selection and sizing going forward. Okay, and one other thing that we've done recently, to finish off some of these soft devices, this idea of these soft devices, is, can we also create microfluidic structures? And some stereolithography methods have actually been used to create microfluidic devices, but the extrusion-based printing has had sort of limited success. I mean, they mostly use some sacrificial materials to create microfluidic structures, but what we can do, what we've recently demonstrated here, is something that I'm pretty excited about. We submitted a patent on this actually, which is, can you build up microfluidics layer by layer in supporting structures, so that to create basically a enclosed structure like you see here. So basically you build up silicone where each additional layer is slightly offset from the layer below it. So you create a fully encapsulated structure of a microfluidic here. And, compared to traditional microfluidics, there are some significant advantages here. I mean, you don't have to go in the clean room. You don't have a big slab of silicone that you're putting down on your sample. You just print silicone where you need it. In principle, this overcomes one of the difficult challenges with microfluidics, which is the automation problem. This is automatable. You don't need sacrificial materials, so that it won't contaminate your substrate. And you can align directly onto the substrate using the printer and print onto any surface. So here we're showing you can print, microfluidics on top of microfluidics to create peristaltic valves, a fully 3D printed structure. But also this is an example of microfluidics that are directly 3D printed on a microfabricated sensor. So the sensor was microfabbed, but then we aligned our microfluidics directly to the chip. And so even aligning a big slab of PDMS to a chip is a difficult task, and this was done, pretty much in an automated process using our 3D printer. And then we flowed in these salt solutions here to show that the sensor worked as we flowed solutions in over the chip. So I think this opens significant potential in taking, the entire space of microfluidics and bringing it to a portable 3D printing platform that can be, now the doctors don't have to go to a clean room. They don't need a big slab of PDMS. Just in the office, they can print any type of microfluidic structure and do biological assays directly in their office, using these simple structures that surprisingly haven't seemed to have been published or developed before. And this also allowed us to do something which has never been done in microfluidics, as far as I can tell, which is basically create microfluidics on a spherical surface. So even though these silicone slabs are elastomers, they're still pretty bulky, and I haven't seen one actually put onto a spherical surface before. And so now you can see we can directly write microfluidics on a spherical structure here. So we're printing two inlets and 2 valves across the 2 inlets directly on this sphere. This is a glass sphere here. So there we're printing the valve on either side. to basically create, microfluidics on any type of surface. So maybe in the future you can print microfluidics on your skin to wick sweat off the skin and analyze sweat. And as you can see on the right-hand side, this is operational. You can see we're switching between the blue and red fluids here directly on this spherical structure by opening and closing those valves. Entire structure 3D printed on a sphere here. So freeform microfluidics. And this sort of gets us to the other topic I'd like to talk about today, which is, can you actually merge electronics and biology together? Can you actually print electronic devices directly on the skin? And so, John Rogers pioneered this sort of tattooing-based approach, this transfer printing approach to taking electronics, peeling it off the silicon wafer, and then printing it onto the skin. And one of the visions that we had is, what if you're like a soldier in the middle of a desert somewhere, and you wanted to print electronics on your skin, for a warfare sensor or a solar panel or whatever, and you just had a printer in your backpack, right? So instead of sort of like a temporary tattoo transfer printing process, this is like the permanent tattoos, because you're using a needle, right? So, can you write electronics directly on the skin? And to do this, we had to solve some significant challenges, because the back of your hand is complex topology, and if you put your hand under the printer, when this needle comes at you, your natural reaction is to want to pull your hand away, and so you have to track your hand so that you can't escape from the robot, right? So, and then of course we also had to develop electronic inks that cure at room temperature so that we could print them on the skin. But I had this amazing student in my group who figured out how to do this and basically incorporate these tracking cameras onto our printing platform, so that we can basically, this is a first step toward incorporating artificial intelligence into the printer, so that the printer now can sense, adapt, and possibly in the future predict the printing state. So you go from an open loop printing system where you scan and then print, into a closed loop system where you're using cameras to, in real time, provide feedback to the printer, so that you can track the motion of a target that's moving and print electronics directly on a hand. And we use these silver-based inks to do this. So this is a silver nanoparticle ink that's incorporated into a polymer matrix, and after you print it, it actually cures at room temperature. So you don't have to heat up your hand, you don't have to sinter the ink, and you can get pretty decent conductivity out of these inks. And but nothing says more than the movie here. So this is one of my favorite movies so there's the hand under the printer, and so we pick and place an LED. That's a commercial LED. We use the printer to pick and place the LED on the back of the hand. These are tracking markers that are used to track the motion of the hand. We do actually scan the topology of the hand before we print, but then the tracking is done in real time. And so this is a silver-based ink that's printed directly on the skin. So basically directly tattooing electronics on a hand which is moving. So this hand is actually moving, and the printer is tracking that motion using the cameras on the printer and compensating for it in order to maintain the geometry of that antenna structure, which is being connected to the LED. I should mention that this printer that we used here is called a Delta Robot, which was a $300 portable printer that weighs about 3 pounds. And so this really is something you can put in your backpack, carry around with you, and we have actually taken it to science fairs and stuff to show kids, take it out and show this tracking system. And so now we can wirelessly power the LED that's after printing the antenna on the back of the hand there. So directly tattooing electronics on the skin, no clean room required. Just using a portable printer and some inks and a sophisticated tracking system that can do this. I should mention that you can actually remove these inks after they dry. You can see we're removing it here they withstand some degree of mechanical deformation, not a whole lot, but so you can move them just mechanically. If you add water, eventually they'll dissolve away, so not so hard to remove. But what I'm really excited about is this thing that we published more recently, which is, there's these classic papers on elastically deformable models. And the thing about deformation is, in that hand example I just showed you, the hand is being treated as a rigid body. So we're accounting for we're accounting for rotation and translation of the rigid body of the hand. But the thing is, there's organs in our body, like our lungs and our heart, which undergo additional degrees of freedom, right? Which is deformation. And so the thing about deformation is rigid body motion basically, the potential energy is zero, right? And then, but the thing is that in the deformed structures, you have energies associated with those deformations, right? And so basically, the question is, can you actually track a deforming target and basically compensate for these higher degrees of mechanical deformation, and then basically print a device which can then sense those deformations of that organ surface. And I see this as sort of a first step toward merging surgical robotics and additive printing of biomedical devices on the same common platform to have a complete surgical robotic solution of both the subtractive surgery as well as the additive biomedical device printing. And this is all accomplished using a feedback loop where we first acquire a set of scans in an offline process in order to reduce the model. Otherwise it's too complex for the computer to process it. So that in real time, we can use this sparse set of fiducial markers tracked by a stereo camera to estimate the parameters of that reduced model, and then basically print onto this deformable surface. So on the left-hand side, actually this is so this movie on the left-hand side, this is a face that we created. It's a face structure in silicone, but then we're printing these silicone features on the face, and you can see it's expanding and contracting. So it's undergoing deformation during this process, and the cameras are tracking those markers of the face and compensating for that in order to print the silicone structures on there. And the needle, you can see the needle never penetrates the silicone. It never pierces the silicone, just like it didn't pierce the hand on the previous thing. We're doing careful tracking here so that it's compensating in real time to not pierce the tissue or the silicone. Here we're actually printing an ionic hydrogel on a breathing lung surface by tracking this deformation. You can see there's only 12 fiducial markers there, and but still we're able to do this tracking because of the offline process that we did first to print this ionic hydrogel directly on the surface of breathing lung tissue here. Okay. And once we cure that ionic hydrogel after printing, we can create a sensing structure. So this is another example of an ionic hydrogel sensor, but the difference in this case is that this is actually a device called electrical impedance tomography device, which has been made many times using conducting materials like carbon black. But I believe, if I'm not mistaken, this is the first time that it's been done using an ionic hydrogel. And the idea here is you place electrodes around the circumference of the device. And so this way, instead of having to print multiple sensors as an array, by printing the electrodes on the circumference and then doing some clever voltage, it's basically like a voltage divider. As you scan the electrodes on the circumference, you can basically sort of create a pseudo array which doesn't exist, which doesn't actually exist on the interior of the structure, and basically map out the deformations. I mean, of course, the spatial resolution is not great, but still you can see that after we use the tracking to print this device, and then after printing, it actually was able to map these deformations in real time using this EIT ionic hydrogel based system here. Okay. So, and I know I need to finish by 10, but there is one last thing I want to show here, which is something which I think I'm really most excited about, even though I seem to be the only person doing it, but maybe in the future other people will too, which is, can you directly 3D print semiconducting devices? So now we want to, can we totally decouple from the clean room? Can we give up the clean room? Can we bring semiconductors into the printing process and actually print not only soft conductors or soft ionic conductors, but also semiconducting devices? And we first demonstrated this in 2014, actually, when we were still at Princeton. We showed that by layering multiple materials, including silver nanoparticle on the bottom, and then 2 organic polymer layers for hole injection, and then a cadmium quantum dot layer as the active semiconductor layer, and then a liquid metal, which is pioneered by Michael Dickey, who also gave one of these EML webinars. We use that as our top electrode. That we can essentially create a semiconducting device where every single layer of the device, the electrodes and the semiconducting layer, are all 3D printed on the same platform. Not the world's greatest device, but it works. And so the trick we use to do this by printing these semiconducting particles is, if you just print them in a solvent, you can see the droplet dries and you get non-uniform distribution of your particles in the drying droplet. So my student actually studied a little bit of fluid mechanics and some basic chemistry, and we figured out that if you use a co-solvent with a lower surface tension, you get these Marangoni effects, which basically counteract that coffee ring effect. And so you print these quantum dots of cadmium selenide, and you can see with the co-solvent solution, this simple chemistry trick, using a co-solvent solution, now we get uniform drying of the quantum dots in order to create a uniform or more uniform semiconducting layer in our device. So we don't do fundamental research really, but we can use tricks from the fundamental world to explore these applications. So this allowed us to 3D print fully 3D print 2 cadmium selenide devices. One is a green, one is an orange. They're different size particles, both cadmium selenide. And of course, being quantum dots, they have good color purity and good saturation. The entire structure is 3D printed: the electrodes, the quantum dots, the top liquid metal contact. And actually, when we got to Minnesota, the chair of my department was synthesizing silicon nanocrystals in a non-thermal plasma. And these silicon nanocrystals are 5 nanometers or less, actually, in size. And so that's actually below the Bohr exciton radius of silicon, which is 5 nanometers. So they emit light, unlike bulk silicon, which has an indirect band gap. So this is an example of we're replacing the cadmium selenide with silicon nanoparticles. So this is the world's first fully 3D printed silicon-based electronic device. So now we're actually taking silicon electronics and integrating it into the printing platform to create a device. And silicon, the band gap is in the infrared, but in the quantum dot, it shifts a little bit into the red. And so you can see in this movie, that's a red LED that's actually based on silicon nanocrystal light emission by incorporating these quantum dots into the structure. So basically taking silicon from the wafer, from the clean room, and incorporating this into the printer. And we can build electronics into 3 dimensions. This is a cube where we basically incorporated 8 LEDs, 8 multicolored LEDs built up into 3-dimensional space in this cube. Again, this is an example of the multi-scale because now we have nanoparticles as the active layer. We have microscale printing, and we have a macroscale device, this cube made of silicone, 1.5 centimeter on each side, where if you probe the different electrodes on the cube, you can see it lights up the LEDs within the cube. Entire structure 3D printed: the silicone, the liquid metal, the quantum dots, the silver nanoparticles. All these distinct materials normally thought of as distinct materials, all coming together on a single platform to print this this electronic cube. And that's an older example, but you know, a year or two ago, we also did not only LEDs but photodetectors, where we can print directly on the inner surface of a hemisphere. So these are entirely 3D printed semiconducting photodetector devices where we're printing these silver nanoparticle, first as the bottom layer, up along the inner edge of this glass hemisphere. And then the next step after this is to, those rings there are so that we can actually visualize light through the device. And then we print this whole transport layer. And actually, Zigong's former student, Xuan Hizao, who also gave an EML webinar, has also published some interesting work on printing P.PSS. This is the semiconductor. It's a polymer blend semiconducting layer for the photodetector. And this is our top electrode, which is this blob of liquid metal. There's probably a better solution than this, but we haven't figured it out yet. And so we call this our bionic eye, because it's an array of photodetectors directly printed on a hemisphere, no clean room required, and then you can image through the bottom to create like a bionic eye. So our 3D printed bionic eye, as you can see, which actually does function. I mean, there's only a few. Right now, there's only a few pixels on it, but you know, you can actually image this cross on the surface of a sphere. And my last slide here just shows multifunctional integration. So here we're actually printing a silver nanoparticle mirror on one side of a piece of glass. And then we flip the glass over, and on the other side of the glass, we print 4 devices. So the outer 3 devices are LEDs, and the inner device is a photodetector. So when the LEDs light up, the light bounces off the mirror that we printed in the first step, and then bounces into the photodetector so that we can image the light that's bounced off. So this may be a first step towards something like you know, a wearable oximetry device or something like that. But you can see each of the layers here printed. The silicone, we use that to avoid shorting. This is the top liquid metal on the device. We print the silver paste on top of that liquid metal to create this integrated structure. And you can see in the right-hand movie that as those LEDs light up, you know, those are the actual LEDs that are fully 3D printed lighting up. And every time they light up, the photodetector that was printed actually responds to that light. So, you know, I'm excited about where this is going. I think there's many applications. We still need to understand better many different things, the materials integration, you know, what really are the important applications? Where do we go from here? You know, but there's a lot of potential here. And the question is, you know, what are the most important problems and what can we do with this emerging technology? And luckily I have some students who are excited to explore this space. So I finished exactly on time. So.
Perfect, Michael.
Okay.
Yeah, can you please unshare your screen so we can see panelists?
Sure.
Terrific.
Thank you very much, Mike, for the very exciting and visionary talk. I'm not sure which YouTube channel you normally follow to get inspired for those ideas. I would like to follow the same YouTube channel and watch them. And now we open up the floor for the questions. Yeah, Sigar, yeah, you have already asked the question about the state of the 3D printing.
I forget that old question. Okay. It's after listening to Mike, I don't want to have it answered. Mike, you touched on something that captures the essence of printing electronics. And that is that the inks can be made on the nanometer scale, right? There may be molecules or quantum dots or so, but the tool to apply them doesn't work on the nanometer scale. And so that puts the burden on printing very fine patterns on the ink substrate interaction. And there are ways of doing it. We did some experiments, I think 15 or 20 years ago. You use the coffee stain effect to get a very fine line, or you actually get two parallel lines from a wider directly printed line. So I instead of wasting time, I want to ask you, what do you see in the direction of printing real electronics, which are on the nanometer scale and which are needed to bring organics into organic electronics? There's no organic electronics really, except for OLEDs. But it would be wonderful to get a complete, I mean, what you're doing just says you would like to have organic electronics. What do you see to get very, very fine lines? That's the biggest issue in the field.
Yeah, I agree. I agree with your point, and I think that what you mentioned with that coffee ring, manipulating that to basically create two lines by basically instead of trying to get rid of those edges, the edges are your lines, right? So, which are probably going to be which will definitely be on a much smaller scale than the 10 micron or so that we're sort of limited to. To be honest with you, I get this question a lot, because I agree with you that I completely agree with you that that it is probably one of the most important problems that people have that hasn't found a good solution, which is how do you really print nanoscale features? But I'll be honest, on our end, we haven't yet found, because we've been working on these applications, a lot of them being biomedical applications, and you're talking about the scale of cells and and tissue and things like that, where at least when we're working with the medical doctors, they haven't come to us and said we need something that's a line that's on the nanometer scale. So I agree with you. It's an extremely important problem, and there's some probably clever ways of doing it, like the one you described, and probably things that I'm not smart enough to think of. But for most of the biomedical applications that we've been working on, we've been mostly focusing on things like cell and tissue scale, where this sort of 10 micron and above has been sufficient. And and this sort of gets back to the question too of what's the killer application space of 3D printing? Because we're definitely never going to compete with Intel, right? We're never going to build a transistor that's 15 nanometers wide, right? But the question is, and then you bring up the organic electronics point, which not only has the size scaling problem, but also the mobility problem. The fact that your mobilities are limited to 1 or 1 centimeter squared per volt squared or whatever per volt second. So then maybe this new niche paradigm, maybe the low resolution, low performance organic transistors are sufficient. And as you said, a good example of that is the OLED displays, where it's driven by an amorphous silicon matrix, because the refresh rate that our eyes is pretty slow, and you don't need the speed, and you don't necessarily need the nanometer scale pixel density. And so we're sort of targeting those applications, like maybe a few devices that stimulate the nerve, like Stephanie's device, but you don't need billions of transistors there to do that. So.
Yeah.
I'm not sure if that answers your question.
yeah, it answers the question. It's completely legitimate, but you know why I asked it. Just quickly, I've been working in electronics for 50 years. Has never been true.
Right.
I've heard many generations of people, Bell Labs lunchtime conversation, there were so many inventions, right? There were always 50% said it will never work, and the other 50% said it will work, and that latter were always right. If it's physically possible, it can be done.
Right.
You just have to figure out how to do it. And physically, it's possible to put a line down from a liquid that is 10 nanometers wide in principle, right? There's no physical principle that says it can be done. And therefore, it's doable. Exactly. I just can't figure out how to do it. No? Yeah. Anyways.
I can't either.
Yeah. James Weaver, do you have any questions for the talk?
No, I think I'm good. I really enjoyed the presentation. Thank you so much.
Okay, no problem. Okay, Haitao, you raised your hand.
Yeah, this is Haichao Han from UT San Antonio. Very nice talk. I think it's very interesting, very great idea using the 3D printing organ for surgical planning. So I have one question regarding you generate organ. So is it possible to incorporate some of the moving parts in the organs? For example, for the heart, is it possible you also put the valve there and the valve can move, and then maybe also add a fluid system. This way you have more functional or mimic functional flow in the heart, and then you for surgical planning.
Yeah, that's a great idea. That's definitely one of our next steps. I mean, can you start to take all these functionality? I mean, so, and you know, one other thing I should mention, these organ models, I see them as not only being used for practice surgery and maybe advanced practice surgery, like what you're describing by incorporating these functionalities, but I see these also maybe in the future as being the replacement organs themselves, because there's all this effort in the 3D printing space on, can we print a liver, right? And so let's print a liver where we print the cells exactly like the original liver in the exact same structure as the liver, try to print the vasculature, all these extremely complicated questions and problems. And my question is, you know, do we trust evolution enough to say that the liver has been optimized to the point where if you couldn't replace it with a artificial liver that maybe works better than the original liver by having silicone and electronics or actuators, as you describe, or something like that. So I see these organ models as not only, you know, now being used for surgical practice, but in the future maybe being the actual replacement organs themselves. And I'm not convinced that printing a cell by cell exact organ replica is ever going to work, or really is the best solution to replacing an organ. You know, why replace biology with biology? To me, it doesn't make sense. So.
Yeah, I think it's a great, you know, long-term goal. You have the cells, their functional organ. Yeah, but I found it's very smart that, you know, for the short term, you can use it for surgical planning. So my question is a short term, quickly, is easy to add like a valve or flow to it? You know, this way, before we reach the long-term goal, you can use it immediately for surgical planning purpose.
Yeah, and this is sort of why it didn't make sense during my presentation, but I showed that actuator, you know, right in the middle of the organ model stuff. And so one can imagine using those actuators as the leaflets themselves, you know, to actuate there. But, you know, the only problem there is it requires like kilovolts of of actuation, you know, so of input voltage, which you know, is fine for an organ model, but not really for a replacement organ. But I think, you know, incorporating some of those actuating structures, as you said, some of the microfluidics, you know, that would be an amazing next step, I think, in terms of more sophisticated organ models for sure. And things again, I think that would be out of reach of a typical Stratasys machine right now. So.
Jun Soo Kim, do you have a question?
Hi, my name is Jun Soo Kim, a fourth-year graduate student in Professor Jigyang's group. Thank you for a wonderful talk. I learned a lot. I have a question on curing system. Could be a little bit detailed, but I wanted to ask about this procedure. So, compared to the plastics, elastomers requires cross-linking to fix their position after printing. And that procedure is usually done by UV curing. However, that process is much slower than printing speed. How do we deal with this speed difference between printing speed and curing speed? Another fact is, what I'm concerned before was, if we add more cross-linker or more initiator in the precursor, the mechanical properties of the precursor becomes worse. So I couldn't use concentration to boost the speed of curing because there was a trade-off. So how do you have any, can you comment on this problem? How do we improve mechanical properties and the curing speed at the same time?
Yeah, that's a great question, because to be honest, sometimes we don't even use UV. Sometimes we just use RTV silicone and then we just let it cure in air, and it can take hours. we can print devices, our semiconductor devices now as well, on the order of maybe an hour, but we have to use heat treatment sometimes with these silver particles that can be on the order of several hours as well, and sometimes even require putting the thing under vacuum and stuff. Now, I agree with you that that curing process is longer than the printing process. However, the printing process itself, I still see as being pretty long, because you compare it to something like photolithography, which in a flash second you can create a billion transistors, right? So, the thing is, this is why I think a lot of 3D printing has focused on customized devices, because we're not trying to go for manufacturing speed overall. We're going for customization, in which case you can sacrifice the speed. But I agree that finding faster curing is a problem, but even just getting faster printing is a problem in itself as well. Even if the curing is slower than the printing itself is still slow. And this also holds true for things like when we're printing on moving targets like the lung. Although actually in that case, the slow speed was the tracking computation, believe it or not the actual speed of the printer. And so, I think that's one of the great drawbacks of printing in general is the low throughput. Whatever step it is, the printing step, the curing, curing the materials, or that's the multi-material integration is a complex problem, but probably can be overcome. But in addition to Sigurd's question about the high resolution, the slow speed overall, the process where we're talking about hours, especially if you're talking about a large organ model that can take 24 hours, is a significant problem. And of course, I mean, smart people like that have developed some of these what is it called, that high the rapid the carbon 3D, right? The DeSimone, Joe DeSimone has created, but those are still sort of the hard plastics. But if we can get to sort of a stage like that with these functional materials, maybe that's the solution, where you're sort of doing the chemistry in real time, using some of these by basically controlling the cooling and the diffusion of the pre-polymer and stuff. So I don't know.
A follow-up question on the computation speed you mentioned. Which one is the bottleneck? Are you using the cloud computing or use the local computing on your desktop?
We use the local computing, but it's actually the tracking. So the refresh rate of our camera is 100 hertz, but it's the tracking, the computation for the tracking. Probably there's more efficient ways of doing it. I mean, we're not computation experts, but the best we could get was a refresh rate of 30 hertz, which is obviously a lot faster than breathing. But and then our tracking error was on the order of a millimeter. So I'm sure with some advanced computational techniques, with people that are a lot smarter than we are and know more computation. Or the other thing is we can also in the future maybe incorporate predictive. With a repetitive motion like lung breathing, the predictive is obvious, but even if it's not repetitive, even if it's random, there's still some prediction that you can do that can help reduce some of the tracking computation and improve the accuracy as well. So, incorporating some AI and predictive might be ways of getting around those problems.
Yeah, definitely. Brian, I've seen you have raised your blue hand for a long time. Thank you for your patience.
Oh, no problem. Michael, that was wonderful.
Thank you.
Look, after you've given us all these positive ideas, I apologize for the fact that I'm going to ask a question with negative connotations. Let's put it this way. I'm curious about the degree of biocompatibility of all the materials that you might like to put into your printed devices. And so to give it a positive slant, I wonder if you could comment generally on the functionalities of a device, such as logic, transistor operation, for example, or other functionality that might present the greatest challenge in finding materials that will do it, that are biocompatible and can exist for a long time in our bodies without doing us harm.
Yeah, it's a great question. So, well, first of all, for that simple circuit, we use silver nanoparticle ink, and silver nanoparticles, despite not being very biocompatible, are the most widely used nanoscale material. They're in our clothing. They're they're everywhere to basically kill bacteria. Of course, also may have a harmful impact on our cells. But to be honest with you, even the ionic hydrogels that we were using, the polyacrylamide, I believe, is not particularly biocompatible. Then in our semiconducting device, we had cad selenide quantum dots, so the cadmium. Then you have liquid metal, which is indium gallium eutectic. Probably not so bad, but probably don't want that stuff dripping around your body. And so, the only answer I can give right now is encapsulation. Basically encapsulating all in silicone. But to be honest, we don't have a good, which is basically like any other biomedical device, right? Everything's encapsulated. But other than that, we don't have a good answer. But the good news is that as more biocompatible materials are developed and biodegradable, the barrier to incorporating those in our printer is fairly low. So if other people work on the chemistries and the materials development, we're showing at least that a broad range of materials and viscosities can be incorporated in our printer. But I completely agree with you that right now we're nowhere near something that's unless we're just printing silicone. But even with that, when we print silicone and cells together, we have to print the silicone and cure it first. Otherwise, the stuff that leaches from the silicone, whether it's the solvent or the platinum or whatever curing agent, kills the cells. So it's a significant problem, and one of many problems I'm sure that's holding 3D printing back from FDA approval, in addition to the customization issue, which by itself is each device is different, so that's a problem too. So I completely agree with your sentiment there.
May I ask a follow-up question then, please? I'm quite out of this field at the moment, so I'd be really interested to hear what you say. Nature itself creates all these functionalities with materials that are biocompatible. Look at us. Is there a concerted or rational effort that could be pursued to find the mechanisms of 3D printing that nature itself uses and the materials that nature uses in those processes and attempt to harness those?
Yeah, and the mechanics people are doing that well, and of course, so I'm teaching right now. I'm teaching Ashby's book. Michael Ashby's book, Mechanical Selection for Material, or Mechanical Design for Material Selection, and so of course the golden rule, the reason why biology works really is because by having the inorganic coupled with the organic, you get the best of both worlds, right? You get the ductility plus the high Young's modulus, so you get improved toughness overall, right? So that's the beauty of biology, is you have that overall toughness by combining the inorganic and the organic. But of course, the problem with electronics is the electronics have the opposite problem. The electronics exist in the other world, where typically when you combine the organic and the inorganic, you get the worst of both worlds. So you combine, let's say, silicon quantum dots with a organic semiconductor, you get the mobility of the organic semiconductor, right, which is the worst of the two, and then you have worse flexibility, or because of the incorporation of the silicon particles. Although sometimes the dielectric constant can improve. I think from a mechanics standpoint, you're absolutely correct. And a lot of the 3D printing people are trying to figure out how do you incorporate the soft and hard to get improved toughness, not only of organic, inorganic, but even of some advanced metal systems, right? Where you can incorporate certain types of alloys to get improved ductility or toughness or whatnot. But from the electronic standpoint, it's a tougher question, because it's hard to really make electronic systems that combine the best of both worlds, which is why the dominating electronic material is single crystal silicon, right, with some dopants in it. So
There's a question from Ali. Unfortunately, his microphone cannot be working. And let me read his question. Probably, Mike, you can read his question as well. For microfluidic printing using silicon, is there any special requirement on the temperature and the pressure that is needed for this device? And also, what's the nodal diameter?
Yeah, the nozzle diameter, it was pretty large, I think like on the order of 100 micron. We did some, because these are lines that are coming together, right? And so we did some burst pressure studies, and the burst pressure is actually pretty good. I can't remember exactly what it was. It wasn't so bad, but of course it's much lower than a slab of silicone because you have these lines that are joined together. And so those are weak points in the structure that can easily, those are failure points, right? If you apply too much pressure. And of course, that's another problem with even 3D printed ceramics and things like that, is you have layers that are coming together. And so it's weaker than a monolithic structure. But, you know, most of the microfluidics is operated well below those burst pressure regime. And so, and then with the overlying valves, which we use for the air control, those can go to higher pressure because we actually encapsulated those with a thin acrylite or something like that to harden it, so we can apply more pressure in the downward direction. So.
Okay, Shao, can you raise your hand?
Yeah, hi, Professor Mcalpine. So thank you very much for your wonderful talk, and I learned a lot and enjoyed a lot. So my name is Shao Ting. I'm currently post-associate from MIT. So I'm working with Professor Sheng. He is occupied, so I'll be here on behalf of him. So my research background is on mechanics of materials. I basically have two questions. So the first question is about the interfacial properties between dissimilar material or two types of materials. I noticed you actually demonstrate multi-ink printing between different materials. You also show actually PDOT, PSS, and the silver nanoparticles, and they assemble together. So interfacial property to me is something like so important to both mechanical properties and electrical properties. So the first question is, can you comment on something like design criteria or how to guarantee the robust interfacial property? I noticed actually Zhigang group have some papers on actually tackling such kind of problems. The second question actually is, I think some other people have mentioned that, so it's about the processing speed of the camera. So that part is, that is actually very amazing to me, because you basically something like need to track the motion of the 3D compact structure. Then you need to do the post-processing. Then the nozzles needed to get that feedback. Then to design the to control for the design motion. So my question is, what's the current something I feel that should have something like a threshold for the motion of your printing target? So what's the current something that threshold based on the current technology in the market? Thank you.
Yeah, so that first question I think is important. If you can send me some of those papers, that'd be great. I've read a lot of Zico and Zos, but not all of them. But you know, if you have some that address that question, that'd be great. But you know, it's not just the material compatibility. The other issue, which I haven't really mentioned, is the solvent compatibility too, because you don't want the solvent of the next layer, you know, to dissolve the previous layer, right? So the solvents have to be orthogonal too. So that's another degree of complication in the problem. And so, you know, it gets to be a fairly significant problem, you know, the more materials you have. But just to show you something here real fast, I'll just share my screen just for a second, just to address this question. So this is actually from our paper. So we break down the current mean time consumption of each step. Now, remember for the deformable printing, the tracking is made a little bit faster by the fact that we're first doing an offline scan. So we first do a scan of multiple deformations so that we can create a reduced model. So that basically speeds things up a little bit. But you can see that each of these is the step of the process. So the feature detection is one of the, basically takes up half the process. But the surface reconstruction is pretty fast because we did that offline scan. And so you can see here that overall we are able to get about 30 hertz of speed. But again, I'm sure this can be improved in many ways by using artificial intelligence or clever tricks that we don't know how to do right now. So and this, by the way, this problem has been in some sense solved. I mean, these deformable models that I mentioned there, it's a classic problem, but also Hollywood uses them. I mean, like Avatar, the movie Avatar, and any of those CGI things. The reason you see those dots on the actors' faces, because they're basically modeling those deformations and motion, and then converting it to a CGI model, right? So we're basically taking that and incorporating that into a. And by the way, that paper, that guy, he's at UCLA, and I believe he works with the Hollywood folks. Basically taking those and incorporating those into a printing system here, because your lungs are breathing, your heart is beating, and so these come into play. Dimitri Terzopoulos is his name. So
thank you. Thank you very much. Thank you very much.
Sure.
Jimmy, you have a question? You have to unmute yourself.
Okay, thank you very much, Mike. Very interesting talk. It actually reminds me of a book I read. This is a book by Michel Aku called Physics of Impossible. And one of the impossibilities is teleportation. So you can deliver something with speed of light, and actually the speed of light is information, right? You can deliver that with information. Then you have your 3D printer. Let's assume that an astronaut is having a heart attack in the space station, and you just send the information, 3D print the new heart and replace this heart. So teleportation. But my question is different. That's science fiction. Actually, this is called, that particular impossibility is called class 1 impossibility. According to him, class 1 impossibility can be achieved in the next 50 to 100 years. So we'll see what happens. But my question is related to what you were talking about before you started your seminar or the webinar, which was what does it take for us to have a 3D printer as a household item, like our refrigerator or microwave oven or things like that? Can you maybe provide some thoughts on the characteristics of these applications that would actually make a 3D printer necessary or very useful, or it becomes a daily item that you use?
Yeah, actually, I think I saw a paper once on your transportation issue where basically I think they were sort of scanning a 3D printed device and then in real time basically recreating it over here. So it's almost like it was teleporting. Or maybe they were etching it away but scanning it while they were etching it, and then like over here basically recreating it on the printer. And so that would be a type of teleportation, I guess. Sorry, what was this? I was just thinking about that. What was the second question?
The question was what kind of characteristics of the application or applications are the right characteristics so that you would have a household item like a 3D printer?
Well, I think the most important thing is that it gets to all the questions that we were asking, because you have to have something where you just hit the button and it just works, right? So you just hit the button and it automatically creates a customized whatever it is that you need. And you can't, the average person at home is not going to be able to solve all these material challenges on the fly. It's going to have to be something where all this stuff is packaged in a way where all the materials problems are already solved, and they just hit play, and it basically creates it like one of those vending machines when you go to, like Taco Bell or whatever, where you can program in, I want vanilla Coke with, a little bit of strawberry, like something like that. It has to be something along those lines where the average person doesn't even have to think; they can just do it, because we have to turn the materials compatibility challenges into, which are important scientific problems, but we also have to convert them into usability problems where the average person can just hit play, and then all those problems are solved in the background. They get what they need as the outcome. Not just the average person at home, but even doctors. I think even if you want to move the printer into the medical space, but here's the advantage. So the way I see it is, let's say you're in a car accident, right? I mean, right now you're in a car accident, you're injured at the side of the accident. The first thing that has to happen is someone has to call 911. So there's a time delay there, and then you have to wait for the ambulance to come pick you up, and then you have to wait till you're in the hospital, and then finally you get treatment. So if you had a printer in the trunk of your car, they could basically just do the treatment directly on the site of the accident. Then that would be a way of skipping all those steps and saving lives there. But again, it has to be a plug and play type of system. Then you could take an Uber home or something.
So maybe let me provide something that I was thinking. So the characteristics of these applications should be, if you look at refrigerator, we use it every day. We open it, close it. So it should be something that you use it almost daily. And the 3D printer would also produce something that you consume or you replace. Two things I can think of. One is food. You press a button, it delivers a hamburger. And the hamburger is not only edible, but also the hamburger has your medicine in it. Whatever medicine you need to eat, the hamburger has that. Not only that, the hamburger may have an electronic device. When you eat it, it monitors your certain heart rate or whatever, right? Another thing we do that daily, we replace daily, is our clothes. So you may have a 3D printer that would produce the new clothes every day. And after you wear it for one day, you don't really need to wash it. You just put it in the raw material. The next day it comes out as the new clothes. So these are, and the clothes would have the electronic device, monitor your all kinds of conditions to make sure that you're healthy. And maybe these are the type of things, maybe features or characteristics that would need for us to own a 3D printer at home.
The other thought I had while you were asking that question is, I just realized, how glued we are to our electronic devices now. How they've created a system basically where you have to check your email every 2 seconds, or you have to check your device. As you said, it becomes like a refrigerator, not only a daily thing, but a minute by minute thing that you can't live without. And I'm, even if 3D printing penetrated the biomedical space, you're absolutely right, which that would not be a daily thing, right? That would be a once every year or once every few year thing. And so, so you're absolutely right that it has to be something that's more frequent. I hadn't thought about that before, but that makes a ton of sense to me. And that may help us, you've given some good examples, but that may also help us pinpoint exactly where this application space truly is. Maybe one of them is because of our tattoo doesn't last very long. Maybe you have to constantly print a new electronic tattoo, because it keeps washing away or something like that. I don't know. So,
thank you. Very interesting talk.
Yeah, great. Tian, you have a question?
Yes, thank you for the wonderful talk. This is Tian Tang from University of Alberta. I actually had a similar question with Xiaoting. I was also interested in knowing more about the interfaces in your multi-material printed structure. So when you print those multiple materials together into a single structure, do you have to worry about interfacial debonding in the structure? So I wonder if you could comment on that, basically on the adhesion between the different components in the structure. Thank you.
Yeah, it's another significant problem. But, you know, so first of all, when we did the ionic hydrogel stuff, that one was okay because we used that benzophenone on the dielectric layer to bond the ionic hydrogel to the underlying silicone, or at least try to covalently bond it, you know, by shining UV on it. For the electronic stuff, turns out not a huge debonding is not a significant issue because of the fact that you know, they're thin layers, but at the same time, the problem really there is the liquid metal on top, and the liquid metal can actually like roll off and create lots of mess and stuff. And so one of the things we've been doing is actually just encapsulating the whole thing in silicone at the end of the process, so that the basically so that the entire structure stays bonded, but also that liquid metal on the top doesn't come off. You know, for the other stuff, you know, mostly it's silicone and cells. And the thing is, when you have things that are high surface area to volume, like cells or nanoparticles, those will just naturally van der Waals adhere onto the substrate because of the high surface area to volume ratio. So, you know, so that's not a huge problem there. But you're right with, you know, if you're talking about layers of, you know, differentiated materials, in some scenarios it may be an issue, especially when you're trying to print on silicone. You know, it works in this particular case of the ionic hydrogel, but for most cases, printing on silicone, because of this so hydrophobic, is a real problem. So,
thank you.
Anastasia, do you have a question?
I do, yes. Hi, I'm Anastasia Elias from the University of Alberta. I really enjoyed your talk, and I thought that you gave us some exciting examples of current and future applications. And I also think you gave us a great picture of the work that you're doing, particularly to advance things on the system sides and incorporating the feedback to enable printing on complex and even moving surfaces. I was wondering if you could share your perspective of what's missing for you on the ink side. During your presentation, I was wondering how often you're able to buy the inks with the functions that you need or functionality that you need off the shelf, how often you're mixing them up in your lab, and what you see as kind of the main gaps in terms of the inks that are available and needed.
Yeah, it's a complicated question, but it's an important question. I mean, the good news is there's a whole host of inks that can be printed. So as materials are developed, probably the barrier to incorporate it in the printer is low. But you see this a lot with some of our devices. We want them to be implantable, and one of the biggest challenges is how do you make something that's both biodegradable and retains mechanical integrity over the lifetime of the device, and then degrades either on command or degrades slowly enough that it's, you know, or that you can tune those, you know, so that's a complicated question. In fact, that question was beautifully exploited by someone named Scott Hollister, who was at the University of Michigan, now at Georgia Tech, who actually implanted these airway stents in children, which were biodegradable. And so what happened is you implant it when the kid is small, and as the child grows and the thing degrades, it actually naturally gets weaker and conforms to the growing child so that they can breathe over time. And so that's a beautiful example where you're sort of exploiting biodegradability, you know, to create a morphing structure, right? But in general, I think that the heart of your question is when it comes to time dynamic structures, which a lot of people term 4D printing, the fourth dimension being time. You know, we have some solutions to that, which I didn't show. We have things like microcapsules that can be ruptured. Other people have created capsules where you have some degree of diffusion control through the capsule, or maybe some sort of other simulation that could release the contents of the capsule and then trigger degradability or trigger migration or trigger differentiation of cells or that sort of thing. I think when you really these time dynamic properties after post printing, right? The time dynamic properties post printing, controlling those are, I think, one of the biggest challenges and one of the most important ones. Where you have to involve chemistry and your understanding of diffusion and multiple materials coming together to really do an excellent job with that. But it has significant implications in the biomedical space. So.
Thank you.
James, do you have any insights to share? Any questions?
Yeah, actually, I do. I really enjoyed the talk. James Weaver from Harvard University. This was more of a comment, but over the years, we've done a ton of work on doing 3D printing of patient-specific models for pre-surgical planning. And one of the things to keep in mind with all of this is that there's not sort of a one-size-fits-all when it comes to matching a 3D printing technology to a specific application. So we, when we were developing these models for the physicians we collaborate with, we'll use half a dozen different 3D printing technologies depending on what the people need. So some people need multi-material accuracy when it comes to variability and modulus within a single 3D print. Some people need things that are watertight because they want to do flow simulations. Some people want things that are mechanically robust so that they can deform the things and see how they behave. Other people are interested more on the data visualization side of things, so being able to print things in full color or with optical transparency or in a multi-material context. So there's not sort of a one-size-fits-all when it comes to a 3D printing technology. So, we always try to, match sort of what the expectations and the needs of the physicians are with the different 3D printing technologies we have available. And that's something to keep in mind if any of you guys are ever interested in exploring this, is that, you can't just go out and buy an FDM printer and expect to be able to meet the needs of all the physicians you're going to be collaborating with. But, it's a great place to get started, especially when people are just sometimes interested in just macro scale 3D geometry that you can interact with in a tangible context. They don't necessarily need full color optical transparency, watertight designs or any of this. Oftentimes it's just a simple geometry that you can hold in your hand and directly interact with. I mean, that's one of the things is that, we grew up in a tangible world. Everyone knows what it's like to interact with a tangible object. And this is something that's very different from interacting, in a digital, or virtual context. So, sort of keeping that in mind is, is really important when you're communicating with the physicians.
Yeah, definitely this idea of mass customization. Although when I visited Boston Scientific, they do have these simulators which are like full screen, and it does feel like you can go and you move your hand like this. You don't even have to touch anything, and the thing rotates, and it was pretty spectacular. If we can merge those with the tangible. But you're right. I mean, I'm not a doctor, but I'm sure the doctors want to actually feel, because they're going to the surgery, they're going to be feeling it at some point anyway, and probably that virtual is not a sufficient match, right? So.
Well, that's also the beauty of this low-cost, widespread 3D printer. It can serve the specific needs of each individual. You don't have to, customize one product that fits all. So that's one unique, leverage for 3D printing. Yakub, do you have a question? Thank you for the patience.
Sure. Yakub Kutsowski. I'm an expert in residence in Harvard, working with Zhigang's team on soft materials, and also former CTO of Cabot, developing a lot of material additives, inks, and different things. And so I'm also kind of nice to see your pitch for University of Minnesota. I'm a chemical engineering graduate from that, so it's a great place, and it's a great collaborative culture and environment. I have two questions. One is more general, and one more specific. So when I think about 3D printing, and and I'm talking about really advanced 3D printing, not kind of little $100 3D printer at home, but really something that you could make industrial scale, or biological scale systems. And typically, what I find is that there are three things that needs to come together, right? And I'm kind of curious in your point in what are you advancing? Because it usually is a printing technology, right? And of course, a lot of the printers been around for a while. Even patents expiring, and so a lot of people coming in, and yet you see people trying to innovate with the way either improve the resolution or improve the range of materials, and so there is a printing technology space. Then there is really important part where I find today is probably the biggest limitation, on proliferation of 3D printing is actually materials, because people really like to have the same parts that they use today, and most of them actually cannot be printed today with 3D printing. You can print it, whatever. It's like you can have any car you like as long as it's black, like Ford says. So it's the same thing. Is that kind of limits what you can do. And there is, of course, an application, right? And so you see, you showed beautiful examples of advancing into different applications and the soft materials and biological materials. But if you look at the intersection of the all three, my question really is, what do you think is the frontier in terms of where are you limited in your ability to advance? Is it more you have the printing technology and materials are there and you just need to adapt them for the application, or you really need to change the materials, and kind of come up with new materials? So the printer technology actually needs to change. So I think that's the first question. The second one is, kind of it's more an application of all these three for the actuators or sensors, right? So I'm kind of quite interested in this DA, type devices, and your thoughts on, trying to make them more practical, right? So when you think about, the voltage requirements, right? So people today solve this voltage requirement usually by creating multi-layer structures. And so getting thin electrodes, multi-layer structures. Do you see this type of, designs being implemented in 3D printing? It would be interesting to hear that.
Yeah, I think your first question is best answered by saying, it's sort of like, it's the same question, I guess, that Apple has been saying, the software and the hardware go together, right? So that's been their philosophy, whereas other people have developed the hardware and other people develop the software. I sort of agree, at least in the 3D printing space, that all these things sort of develop together, right? It's not, I mean, there are people who are experts in one or the other and have developed them. We sort of taken, I guess, a broader approach where, but maybe less deep, I guess, but a broad approach where sort of we'll develop, let's say, this deformable paper, I think, is a good example where we developed the deformation tracking, but then at the same time develop this EIT device, to bridge that. And that's the sort of thing I like to do. It's kind of take these things and sort of bring them together. But I completely agree that there also needs to be deeper ones where someone really takes the deformation, let's say, tracking, and really goes thoroughly into that. How does one improve that? The questions that have been asking, how does one improve the tracking speed and these sorts of things, these, predictive and these sorts of questions that we're not so good at answering. But that's the beautiful thing about the platform is there's space for all these different types of personalities, depending on if you're someone who likes to focus on this particular problem, even there's fundamental questions, I believe, as well, in there. Now, the second question that you asked is interesting. I mean, because now you're sort of we're back to the question of what's the ideal actuator look like, right? I mean, because, so the downside of the ionic hydrogel base is, the high voltage, right? And then the downside of PVDF is the low piezoelectric coefficient, right? And the downside of the PZT is the high Young's modulus, right? And then and it contains lead. And so I'm not sure I have a good answer to those questions. What does the ideal actuator look like? Actuation has always been a tough thing, and we showed one example, but again, that was, very high voltages required for that. And the only way we were able to prevent breakdown is by adding those barium titanate particles. It didn't work without it. And then we've tried some of the PVDF stuff where people say that they print PVDF and then the shear actually aligns into the beta phase or whatever it is, to get good piezoelectric properties, but we didn't really have much success with that. And so, I'm not sure actually. It's the same question that's been asked in the energy harvesting space for a long time. Why don't we have PZT in our shoes harvesting energy for all these same reasons? It's just the materials. Each of them has a significant downfall. And this is another example of where merging materials doesn't give you the best of both worlds. People take PVDF and they mix in PZT particles in it, and your piezoelectric coefficient doesn't go up at all. You've just made the structure less compliant. So I don't know. That's a really tough question. Layering, as you said, maybe an answer, but then you have a thicker structure, right? So you get less deformation. So it's a really tough problem. I wish I knew the answer.
Thank you.
Tang, you have a question?
Hi, Sheng. Thank you. Hi, Michael. Thank you very much for the wonderful talk. I enjoyed your talk very much. So actually, I'm now an assistant professor at Michigan State. My group now mainly working on the printed electronics and software robotics and some composite materials. So I have some questions here. Maybe I'll ask one. Okay. So because in the biomedical applications or some food applications, if we use in our electronics, printed electronics, we inevitably to use some nanomaterials, either nanomaterials, nanowires, or nanotubes. So these kind of materials, people have some safety concerns, and it may have some migration and issues and toxicity. So actually, this is something similar to the sintering conditions. We need some heat sintering process, or the UV treatment. So this, what's your vision for such kind of the problems, and what's the perspective in the future? Thank you.
Yeah, I mean, it's a problem I mentioned before. Where I mean, silver is one of the most widely used, or the most widely used nanoscale material, and it's in all of our clothing, and but it's actually not questionable how toxic it is. So I think nanoscale material toxicity is always going to be a problem. Nanotubes and whatever. I mean, you're talking about things that are small and can accumulate and perhaps pass through blood-brain barrier, or maybe be detrimental to cells or leach atoms or whatever because of the high surface area. So it's a problem sort of independent of the 3D printing stuff. But at the same time, we have options like encapsulation. We have options where if someone develops better materials or more stable materials, then we can probably pretty readily incorporate those in the printer. But our only real solution right now has been encapsulation in silicone. That's just been the only go-to that we've been able to find that works well. And that's not just to protect the biology, that's also to protect the device itself, right? So I wish I had a better answer, but it's a tough problem.
Yeah, thank you.
Zigang, I'm sure you have questions to ask Mike. You have to unmute yourself, Zigang. Zigang, you have to unmute yourself.
Sorry. Yeah, brilliant talk. So you have been focusing your attention on developing new applications. That's exciting. Get people's attention, and also just explore the cutting edge of the technology itself. I'm sure during this process, you must deal with a lot of practical materials problems, mechanics problems. We just want to have a few short questions, so to just illustrate the issue. So maybe people, my group, for example, be interested in mechanics and materials problem, not necessarily have the bandwidth to deal with a full-scale biological instrumentation problem. Now, simple one first. Now, you use polyacrylamide, right? So I'm sure you do polyacrylamide in monomer form and then deposit. Two questions. That monomer, of course, is very poisonous. Second question, that monomer, if you do that, you probably have very oxygen-free environment. How do you think about these things?
To be honest, right now first of all, the monomer we do use the monomer. And we do almost all of our printing in open air. So my students wear like ventilator masks, basically. We don't have the printer in any hood. Even when we do the bioprinting, we don't have the printer in the bio hood. We add antibiotics to the solutions to keep the cells from being contaminated, and we wipe down the printer. But I think the ideal scenario is to have the printers probably in a controlled environment. But then we're getting back to like one of my talking points is, can we put this in the doctor's office? Can we take this out of the clean room? Can we get right? But you're absolutely right. Is once you start those questions, then you get to the questions of what about chemical safety? What about biological viability? What about human safety? And what about materials dissolving other materials, and what about UV cross-linking, exposing people to UV and things like that. And so, again, this is why we need the mechanics. This is why we need the chemistry people. This is why we need all these developments, because we're using what's available right now. But this is one of many reasons why this is not in the hands of the average person yet. But let's say that all these problems were solved, right? Let's say that we did solve all these problems tomorrow. We have the ideal materials, which, by the way, I mean, as I mentioned before, I'm teaching material selection, Ashby's book, and the ideal material never exists. Keep in mind, right? So, I mean, when you select a material for an application, you're selecting the best out of the worst, basically, right? You're right. In most things, you're never getting the ideal where you want to be. It doesn't exist. So you have to choose, the best that you can do with what's available. But even if all these problems were solved tomorrow, let's say we can make perfect transistors, we can make whatever, perfect biomedical devices. I still wonder, we still have to ask the question, are we serving a need, right? Let's say we do that. Will the average person still go out and buy the printer? Will the doctors buy these printers? What will they be using it for? I think maybe we need to do a better job starting with that question first, and then working our way back to what are the best available materials at the time, and then maybe that'll lead us to the better outcome, and then that way we're focusing on specific material challenges, problems, rather than sort of a more broader and less defined problem, which will always exist, right? So.
Yeah, I agree. So one has to focus on these immediate problem to make people interested in the technology. I interact with a doctor. You probably don't know his work. He actually published a book, or on a use case you touched upon. He is a surgeon, heart surgeon, actually using minimum invasive technique. So one thing that worked really for him and for people like him is to do 3D printing of the heart or whatever you're going to do surgery. You print that specifically according to the medical images of that patient. And then you not only practice on these things, you actually just show to the patient. That's terrific. So he actually wrote a book, have many cases why these things are useful. I don't know if you have seen that. So but back to the materials problem, because I guess ultimately many researchers also assume, perhaps is also correct, that 3D printing or additive manufacturing in some form will be quite pervasive in future. So it is the right time to invest time to study basic material science problem, mechanics problem. So, for example, now I'm actually surprised in the polyacrylamide case, just specific, you can actually do this in open air, do polymerization. We also always had trouble do it in open air because of oxygen. We have to, do you have a problem at all?
I don't think we had, to be honest, I'm not sure. I'd have to check with my student as to how they got around that problem. But I mean, maybe we used a lower. Well, first of all, we used barium titanate in it, so maybe that was part of it. But maybe the ratio of the cross-linking agent was smaller. But we also had this. We also did actually add polyacrylamide as a thickening agent itself, so it wasn't pure monomer. And then we also had, So but let me ask my student about that and get back to you, because that's an important question.
Yeah.
So.
Yeah. Another this smaller question, but probably illustrates a generic issue in our body, right? You talk about a solvent contamination. Our body has one solvent, that's water, so it's contaminated everywhere.
Sometimes alcohol as well. Sometimes alcohol.
In the specific case using ionic hydrogel, you also need to have a dielectric. In your case, it probably is PDMS, right? It is a PDMS. And we also did some measurement, just find, of course, water actually permeate, water and ion permeate from all dielectrics we can find. In the thickness, ultimately relevant for many applications. You probably haven't handled these problems at all, but just a generic question. You raise yourself, solvent contamination, especially for elastomer soft materials. Do you have any general thought about this kind of thing?
Well, okay, so let's say for the ionic hydrogel, we used two solvents. We had ultra pure water and we had ethylene glycol. But most of the solvents we've been using have been, we use different solvents for different applications. With silicone, we don't really even use a solvent. We actually just use silicone grease and RTV straight from the bottle. So there's no solvent there, actually, solvent free. So when we're printing the semiconducting layers, we use the solvent there as that co-solvent that I mentioned before, the dichlorobenzene and the toluene, and that just evaporates, after we print it because it's a small amount. We do have issues when of course, there is a solvent in the silicone itself, and so that will actually basically kill the cells sometimes when it leaches from the silicone. And so, so there are definitely some issues there in terms of material compatibility, killing cells that are next to it or dissolving other materials that we don't want to dissolve, or controlling the evaporation, right? So, of course, all of these are problems. And, the oxygen problem, sorry, my battery's almost dead, so I'm just plugging in. The oxygen problem is also important too, not just for the polyacrylamide, but also we do keep the polymer semiconductors that we use in the glove box, when not in use, and try to minimize air exposure there. But even then, we do still print them out in air, So I think it's the time component too, which has an effect. So, like the time of printing. Just plug in real fast.
Thank you.
Sure.
So Zhigang, the comment I was making was our human body is mostly water, but sometimes we also have alcohol.
Yeah, alcohol. Also, of course, in your stomach, there is a high acid. The biology must have solved that problem.
Yeah, it's amazing. It's a magic. Li Qing, you have a question?
Yeah, thank you. So actually, I'm not in the chemistry field, so I'm just general mechanician. So I have a very general question. Maybe it's just follow up the Zhigang's comments here. So 17 years ago, I attended a talk given by Huajian Gao. Then he was talking about the ability of the bone. He in his experiment, he said, when we take the bone out of the human body, we test the ability of the bone. Actually, it's very weak, very easy to be broken. if we do this the uniaxial compression test. Yeah, but when the bone inside our body actually is, it can bear the very higher compression stress. So then he gave us the explanation is that, then he said, because of the softer material around the bone, like water or oxygen or some soft tissues could strong this bone tissue inside our body. So do you think in your 3D printing, printing technique, do you think you can print out the real bone, not just the bone outside of the body? Thank you.
I think people have tried that. I mean, again, it's this sort of merger of the inorganic and the organic. I did actually see Zhigong's plastic bag thing where you have anisotropic, you have mechanical, for some reason in plastic bags, which is just basically just polyethylene. You have tears easily in one direction and not the other. I didn't quite understand that one, but no. So I think there have been people who have tried to look at bone and ceramics and that sort of thing, and to be honest, I don't know that much about it. But this may also be one of these scenarios where you don't necessarily need to create a bone made out of hydroxyapatite and protein. You may be able to make some artificial materials, synthetic materials, and basically combine them to produce the same outcome, right? So
yeah, Li-Chen, I can have some comment. So Mike, you probably will also be interested. So you keep talking about integrating inorganic material and organic material, maybe for toughness or maybe for some mechanical function. Actually, it's interesting. Recently, we kind of rediscovered this. The problem or the idea or what makes it work is not really inorganic or organic. It's really hard and soft. So if you have a mixture, you can easily create very tough material. We have several recent demonstrations. I can send you a couple of papers. It'll be very trivial for you to print something. One specific example is we can use a little harder elastomers, such as PDMS, harder elastomer, with a hydrogel as a matrix. That material is much tougher than PDMS itself. So,
really?
Oh yeah. So
okay, because of this, because I wonder why that, because it's such a low Young's modulus.
Yeah. So the analogy is something familiar to you, right? For example, today, airplane has a composite material.
Right. So it's spring constants in parallel versus spring constants in series? Or?
Yeah. So just think about it as a composite. The carbon fiber itself is really brittle. But once you put in the epoxy matrix, that composite is very tough as metal. Right. Yeah, it's possible. The principle is old. We just rediscovered this recently in developing soft material. You can easily develop a very tough soft material with any material, essentially.
So when you do the hydrogel silicone, is that as a uniform mixture or is that in layers, or you've tried both?
We tried a number of things. One is just a fiber. We make PDMS into fiber and then use hydrogel as a matrix. We create adhesion, also use benzophenol. Right? So hydrogel matrix and polyamide, PDMS as a fiber. That material it's enormously fatigue resistant as well. You can even do cyclic loading. The crack cannot grow.
Really?
Yeah.
Because the fiber blocks the crack propagation?
Yeah, but fiber is a PDMS. PDMS suffer fatigue like crazy. If you just make a little cut, you just play with the PDMS, the crack just grows. But if you make it into fiber form with a soft matrix, that material is fatigue resistant. Again, the principle really is old composite principle, because but people probably didn't think about applying the same principle to soft material itself. All it takes is a contrast of material modulus. It's not organic or inorganic, or it's not even hard or soft per se. It's just, yeah. So, sorry, it's just a direct response to Li Chun's question.
But this actually also may get back to the biodegradability question. You may have a biodegradable material where it's reinforced with silicone, but then after the matrix degrades, the silicone is small enough that it just passes through the body, right? But at least it reinforces the biodegradable material as it's degrading.
Yeah, we're actually doing that now.
Oh, okay. That's your next paper.
Yeah. I'll send you something really trivial for you to do. One thing we did, we haven't really published. I saw you also do heart valve, right? Heart valve, a critical requirement is a fatigue resistance, because it's not about need to do this a billion times during people's lifetime. Biological tissue really is fatigue resistant. Heart valve. For most people, heart valves survive for the lifetime. But when you make it using regular soft material, that soft material cannot last. But once we print it with a hard and soft, stiff, both are soft material, but one material is a little harder than the other material. That material is fatigue resistant. You can do this forever.
As long as your interface is good, right? It has to be a good interface.
Yeah. We use benzophenol or a number of other things, because the interfacial adhesion between soft material, including hydrogel, has been advanced tremendously in recent years. So Shaoting is an expert on this kind of thing. There are several groups really made this happen. You can essentially stick anything to anything now. Yeah.
So actually, let me ask you a question related to that. It's the hard and the soft, but I guess another question I have is, you also have anisotropy there because you have long fibers in the matrix. Does the anisotropy contribute to the fatigue, to less fatigue, or the anisotropy doesn't affect the fatigue performance at all?
It's not about anisotropy. Really, it's about a contrast of a modulus of two materials. For example, we also made a hard material into a lattice. It's an isotropic lattice, and then fill the space, open space, with hydrogel. That material is also fatigue resistant. Yeah. I'll send you the paper. We have several recent papers talking about, I'm glad you're really interested. But once again, your talk is just amazing. I hope our students, mechanics students, get inspired. These things might be useful for other people. Because you're really interfacing with industry and also particular use case that I think really is the right thing to do if you can do it with that bandwidth. We don't have bandwidth, but you do.
Thank you.
Yeah, Mike, very inspiring talk, especially this soft printed prostate, right? And he even demonstrate the suturing on this prostate organ. However, biological tissues are inherently heterogeneous, which means even for the same organ, the fat concentration, muscle fiber orientation, anisotropy, vessel distribution, they are all different from place to place, right? How do you handle this? What's your envision and thoughts on this one?
We're thinking about that. But so, I mean, there was, because also the tissue is hyperelastic or strain stiffening, right? We also did not, we haven't demonstrated that either. So the anisotropy, the strain stiffening behavior, incorporation of advanced functionality like it was described, like actuators, I mean, these are all, I think, reasonable next steps, not just to creating organ models for surgical practice, but maybe even creating synthetic replacement organs for the original organ. So.
And going back to the the discussions we had before your talk, you mentioned the household adoption is one of the greatest challenges for the 3D printing field, right? I would say that one is probably more on the marketing side or more on the commercialization part. We are engineers, scientists. What are the technical challenges that hold this great tool back from being adopted by the household? Let's not worry about the cost or whatever those stuff. What are the things that the scientists can make a little contribution to?
Yeah, I think you're right. I think the thing is though that because the technical challenges basically span chemistry, mechanics, computer science, biology, and because they span so many things because of the sort of potential really of the platform, that in order to focus on a problem, you do sort of sometimes have to start on the application end and work your way back to know, because you can't tackle all those problems at the same time. No one person can. And so that's why we sort of work our way back from the use case back to the specific technical challenge, that hopefully still advances the field as a whole, right, by solving it. So so that's why I raise those questions, just because the breadth of challenges here is so enormous that at least by focusing on an application, you can work your way back to at least carve out a slice of things that not only advance the engineering, but also advance some particular application which didn't have a previous tool to create what was needed there. So.
It turns you have some direct experience. So you bought something for your son, and you're pretty technical.
Okay. I have to give you one example. Yeah, thank you for asking this. By the way, Mike, amazing talk. I really enjoyed, and also the lively discussion with the panel as well. Maybe elaborate a little bit what we discussed at the beginning before the webinar on this. How come this 3D printing now is available on the market? It's actually not that expensive. It's as expensive as other household electronics, right? The fridge, the dishwasher. I can actually give you one example. A few days ago, one of the parts, the part in my fridge actually broke. It's a plastic part, okay? Typically, you have a couple of options, right? So you either call the fridge company, the customer service, and pay $50 for that plastic replacement, right? Or you can drive to the Home Depot and buy a replacement. It might be cheaper. But now here is the pandemic factor. Now, if this happens last year, I probably would drive to the Home Depot to buy a part to replace it. Now, I ask myself, should I go over there, buy a little part and, with the potential exposure to the public, is that really necessary? So maybe in this case, I'm putting this as an example that if, for example, this plastic replacement part, the company can put the 3D printing profile over there, I can actually use the 3D printer my son has, print it out. Even though it's not that cheap, but I mean, this problem is actually not unique and not just for me, because this probably happens in every household multiple times during the year or during the service of each individual electronics over there. So I think that could be something the 3D printer can be used for to solve this. So the daily operation of the household, those issues. That's just one single example I can think of. Again, this has something, as Sheng mentioned, this might be a cost issue or other technical issue, but I think as engineers and the scientists, what we can help here is really look into why it takes still not that low cost to make a spare part like this, right? So the material cost, equipment cost, and also the speed. I think the speed is so far, at least at this low end 3D printer everyone can afford, it's still very slow. To be honest, and my son, he was printing a piggy bank, a very small size piggy bank, for like 5 hours. And I was joking that, okay, you need to fill up this piggy bank like 10 times to cover the cost of making this piggy bank. So it's just some rather random thought, but I think this is relevant to the discussion here, hopefully. Sigurd.
Yeah.
Sigurd, you are muted.
Sigurd.
Standard problem. Because we're getting into general how is life questions, I ask you the following. You rely extremely on collaboration with medical doctors or specialists, right? And I find in this work, everybody must have found this, is interfacing with other communities is very difficult because they use different languages. You have to learn their language. It takes you 3 years to realize that substrate for somebody who works in biology is completely different meaning from the substrate for an electronic device, right? What's your experience? I mean, you emphasize, and you know, when I visited already, when I visited you, you emphasized the building is across the street, there are people who are interested, but it's always a subset. How do you find them? How do your students learn to talk with their students? Do you have any advice on that?
Well, I think the good news is because everything's so close together, we meet fairly frequently, but I've been surprised. I mean, these doctors, we're doing one thing where we're trying to look at some of our photodiodes on the skin for UV exposure. And this guy somehow knew, or picked up fairly quickly a lot of the electrical engineering and the device parts of how a photodiode works. So I mean, these guys are just really smart people, and they're so open-minded here. I'm not sure if it's that way at all universities with medical schools, but here it just seems they're just so open-minded to the technology. And but the interesting thing is, part of it may be the culture here, because you look at something like Medtronic, which is basically founded on the pacemaker. The pacemaker is basically, in a sense, an electronic device. I mean, it's essentially a battery and a pacer, right? So I mean, it's so like it's almost like our we're not a pharmaceutical environment. We're actually like almost like a electronic or bioelectronic type of environment that we exist in. And so maybe that sort of permeates the culture here, where device technology is actually sort of inherent to our solutions, and therefore robotics and electronics and mechanics sort of permeate the bio here, rather than things like pharmaceuticals and drugs and that sort of thing. So it's just an interesting culture. I mean, of course, no one ever thinks about Minnesota, on a daily basis, but then you move here and it's like its own universe of opportunity that I wasn't expecting and was fairly surprised about, especially, I didn't even know all these Fortune 500 companies were all headquartered here and that sort of thing. So,
well, I just purchased a 3M half face mask because I'm trying to prepare for long distance flights. So Minnesota is on many people's minds, when you think of 3M only.
Yeah.
Yeah, actually, Twin Cities is one of the most important biohubs in this country.
It must be that there's so much electronics in Minnesota already, the corporations, that it's kind of obvious there. That's not true in many places of the country, right? Here in the New York area, you don't think automatically of making money with bioelectronics, but in Minnesota, you know, you can. No?
That's right.
Hong, you have any questions, comments? I've seen you have been very quiet and patient.
Thank you. Thank you for the wonderful talk. And it's very enjoyable to listen to the discussion from panelists. So I actually feel uncomfortable to ask a question because my question is very irrelevant to your discussion. I feel everyone discussing the very important question about the development of the 3D printing in current stage. But my comment or question is more related to my personal curiosity. So first one is I noticed that most of the 3D printed structure or models are in very regular shape. For example, it's a tube or a cube, and when I look at it, some structure with very weird shape, I was wondering whether that can be printed by the 3D printer. For example, when I look at the dandelion, so dandelion can fly with the wind, and that's fluid dynamics things. I was wondering if I can graph that dandelion on the micro beads robot made by the rubber wood. So that could be right powerless. But I feel that the shape of dandelion is maybe it's hard to done by the 3D printing. So I wonder whether it's possible to do some weird shape printing. So second thing I want to talk about is my understanding of 3D printing maybe is not a very realistic at this current stage. I was wondering in the future, right? The resolution of the 3D printing must be enhanced, right? So what's the limit? So for example, if we enhance it to the micro scale or 100 nanometer scale, maybe we can do something like arrange the microstructure of the material. For example, for polymer, we can print polymer chains, bundle of polymer chains or fibers with the radius of 100 nanometer. So we can tune the microstructure of materials. So the third comment is, I remember many years ago, the IBM actually arranged the several atoms into a human shape. Right? So my crazy understanding of the 3D printing is, in one day maybe we can print monomer directly. For example, in medicine, we want to synthesize some medicine, right? So there's a lot of steps. Why not you just put the atom together and we got them, that molecule we can use to cure the disease. This is just my illusion. Thank you.
Oh, sorry, go ahead.
What was your question one?
Question one is that possible to print some weird shape like a dandelion? Yeah.
So I think, that's an area where someone like Katya Bertoldi really excels. She, we're not really making sort of advanced mechanical structures like auxetic materials or fractals or, but there are people out there, I think, because I guess Katya gave, she's on the board, right? And then she also gave one of these EML seminars. So, she's someone who really excels on sort of making, pushing the limits of these mechanical structures, whether 3D printed or not, and seeing how they behave and some of these foam type of structures with different shapes and on the interior and stuff. So I'm sure that can all be done. I think from a mechanics standpoint, like there's people much better than I am who who study those things and bite stability and all those things. So she's pretty amazing in that realm.
Also,
and then
Julia Greer also at Caltech. She's also doing that.
Yeah, the trust.
Yeah, with Hughes Research, right? HRL. And then I guess your second question was actually related to Sigurd's question. Actually, when I think about it now, I mean, when you look at the photolithography, the lights, can't make 15 nanometer features, but still they make them. And they use it by using different aperture lens, but they also use, I think, like clever etching techniques and tri-gates or whatever, which I guess would be like the equivalent of what Sigurd mentioned before of sort of exploiting coffering effects to get edge features that are much smaller than the width of the line feature itself. So maybe techniques like that, like combining subtractive etching in a clever way, like the semiconductor industry does, to get well below the diffraction limit. Maybe something like that could be used here to get well below the nozzle limit, right? So I guess that would be another way of answering that question. And then your third question was
one atom at a time, one mono.
Like Don Eigler, right? So that's Don Eigler at IBM that pushed those atoms around and created like quantum wells and stuff. I guess you could do something like, I mean, in principle, you can mount a molecular beam epitaxy fusion cell or something on your printer, and I don't know, maybe that would work. So maybe that would be the solution, is to have like an fusion cell as one of your heads next to the, where you're basically doing molecular beam epitaxy on a printer or something. But molecular, I mean, it's already a printer in a sense. I mean, you have shutters but the key thing there is controlling monolayer uniformity and making sure you don't have defects and atomic coverage and things like that, right? So I'm sure there's atoms on our surfaces contaminating our surfaces regardless.
Then you have to use a carbon nanotube as the nozzle to allow those single molecule pass through one by one.
Yeah, well, actually, that's a good idea. I mean, because you go back to my PhD advisor, Lieber, right? I mean, one of his things that he did once was the AFM tip, he put a nanotube on the tip of the AFM tip to get even, I guess, better resolution, or use it as even for doing some sort of chemistry or something on a tip. So I guess having like a nanofluid, but then the pressure, the possibility of breaking with collisions, or the pressure that's required, maybe, I'm not sure, capillary effects or.
Well, there are people reporting passing through of water molecule inside the carbon nanotube, but they can count it. So there are some papers on this already. Yeah.
All right.
Zhigang, you have any final concluding remarks?
No. So, Sigurd, any parting wisdom?
Yes, I thought that was a really great presentation. That's my wisdom.
Thank you.
Michael, thank you very much. And I think you are opening a field that is going to hang on. This household printer idea I am not so fond of, because everybody who has a home workshop will get a 3D printer. So 1% of the population will get it. But remember, the electronic devices that are catching on, they're all passive. That's why they're spreading so easily. All right, you don't have to do.
You like RFID tags? You're talking about RFID tags?
No. The phone. It's a passive device. It doesn't actually force you to do anything. But the printer is a maker device, and the only making that happens in a regular household is in the kitchen.
Right.
And even that is drifting away. You're getting catered. So I think the people who have a workshop at home will get the printer. It's about 1% of the population, I think, or perhaps a little more. And so it has a very large market, but it is not the entire population.
Yeah, that's a good point. And that gets to the question of where's the money, or is there money? Is the money in the materials that's sourcing the printer? Is the money in building the printer? Is the money in creating the device and then just sending it, or is the money in the person buys their own printer? And related to that is, the question of what you're just saying there. Does someone buy the printed device, or do they buy the printer itself to print the device? And but the question may also be, is the money that's currently in the biomedical industry going to be dissipated because people buy their own printers at home, and so that gets basically democratized to.
I don't know. It always needs expert. You know what Tang just described? Tang, that may happen. There may be little shops in the neighborhood where you say, "This is the plastic part that broke in my fridge. Can you make it?" Because there's lots of skills involved.
My son ran a small business in the neighborhood.
Yeah.
Another model.
Anyways, Mike, that was really great, and I wish you, and I think everybody here wishes you the best of luck in pursuing what you're doing. This is a highly productive area.
Yeah.
Thank you very much.
Thanks a lot. Yeah.
Thank you, Michael.
Yeah.
Thank you.
Thank you.
Thanks.
All right. Bye.